Hello there, and welcome to Just About Earth, where curiosity settles in softly and the world's biggest questions are explored at a pace slow enough to breathe along with. Tonight, or this morning, or perhaps somewhere gently in between, we're going to wander into the story of a winter storm that arrived with a name, a presence, and a ripple of cold that travelled farther than most of us expected. Its name was Fern, and for a few days, it became part of conversations at kitchen tables, weather updates on glowing screens, and the quiet observations made while looking out of frosted windows. Before we ease into what truly shaped this storm, let me ask you something simple and familiar. Where are you listening from right now? Are you wrapped in a blanket, sitting at a desk, or perhaps already drifting towards sleep? And what does the air outside your window feel like at this very moment? Is it still, warm, buzzing with summer insects, or heavy with winter's hush? It's curious, isn't it, how a story about cold can be heard from anywhere in the world, across time zones, across climates, across entirely different skies. If you find this little corner of calm helpful, if the slow unfolding of Earth's systems brings you a bit of peace or gentle curiosity, I'd be grateful if you gave the video a like, maybe even subscribed. It helps this quiet space reach others who might be looking for something thoughtful to listen to as their day winds down or their night begins. Now let's take a breath together and step into the long path that leads toward Winter Storm Fern, not rushing, not chasing headlines, but simply following the way air, water and energy moved across a living planet. Storms don't begin with thunder or snowfall, they begin in places most of us never see, in invisible boundaries between warm and cold, in subtle bends in high-altitude winds, in oceans that quietly store heat like vast, slow-moving batteries. Long before the name Fern appeared on forecasts, long before snow piled against doors and wind pressed against windows, the atmosphere was already arranging itself, piece by piece, like a complicated puzzle being solved without anyone watching. High above the surface of the Earth, far beyond the reach of birds and airplanes, rivers of air flow endlessly around the planet. These aren't rivers you can see, but they are as real as any waterway cutting through land. One of the most important is the jet stream, a fast-moving current of wind that snakes its way around the globe, separating colder air to the north from warmer air to the south. Most days it stays roughly in place, wobbling gently like a loose ribbon in the sky. But sometimes it stretches, dips, and bends in dramatic ways, and when it does, it can carry entire weather systems along with it. Somewhere far upstream in that invisible river of air, a subtle change took place. It might have been a surge of warm air rising over an ocean, or a pocket of cold air slipping south from higher latitudes. These shifts are small on their own, almost unnoticeable, but the atmosphere is a system that loves to connect things. A change in one place often leads to a reaction somewhere else, like a long chain of quiet dominoes tipping one after another. Closer to the surface, the land and the sea were playing their own roles. Oceans don't just hold water, they hold warmth, stored from months of sunlight. Even in winter, the surface of the sea can be significantly warmer than the air above it. When cold air passes over these warmer waters, energy moves upward, rising into the atmosphere. This rising air can help lower the air pressure below, and low pressure is one of the essential ingredients for building a storm. Pressure, in a way, is the atmosphere's version of balance. High pressure means air is pressing down, sinking, and often bringing calmer, clearer weather. Low pressure means air is rising, pulling in surrounding air to fill the space it leaves behind. That inward rush of air creates wind, and when enough moisture and energy are involved, it can also create clouds, rain, snow, and the kind of swirling motion we recognize as a storm. As these conditions quietly aligned, a developing low-pressure system began to take shape. It wasn't dramatic at first. It might have looked like just another patch of unsettled weather on a forecast map, a cluster of clouds forming where warm and cold air met. But the atmosphere has a way of amplifying certain patterns, especially when the timing and positioning are just right. Cold air, dense and heavy, tends to slide underneath warm air, which is lighter and more eager to rise. When these two meet, the warm air is pushed upward, cooling as it climbs. Cooler air can't hold as much moisture, so the water vapour it carries begins to condense into tiny droplets or ice crystals, forming clouds. With enough lifting and enough moisture, those clouds grow thicker, taller, and eventually heavy enough to release their contents back to the surface as rain, snow, or ice. Somewhere along this boundary, Fern began to find its footing. At first, it was just a developing system, not yet a storm with a name, not yet something that would close roads or cancel plans. But the ingredients kept coming: moisture from the ocean, cold air from the north, a supportive bend in the jet stream overhead that allowed the system to deepen instead of being pushed aside. One of the quiet forces at work here is something called temperature contrast. The bigger the difference between warm and cold air in a region, the more energy is available to fuel a storm. It's a bit like stretching a rubber band. The farther you pull it, the more energy is stored waiting to be released. When a strong contrast sets up between air masses, the atmosphere has a lot of energy to work with, and storms can grow stronger as a result. As Fern continued to develop, that contrast became more pronounced. To one side, relatively warm, moist air flowed in from lower latitudes or over open water. To the other, colder, drier air pressed down from the north or from higher elevations. The boundary between them sharpened, and the low pressure centre at the heart of the system deepened, meaning the pressure dropped further and further. Lower pressure doesn't just mean stronger winds, it also encourages more air to rise at the centre of the system, which leads to more cloud formation and more precipitation. The rising air cools, moisture condenses, and the process feeds itself, drawing in even more air from the surroundings. It's a self-reinforcing loop, one that can turn a modest weather system into something far more powerful. While all of this was happening, people on the ground were still going about their days, commuting, cooking, checking their phones for brief weather updates, maybe noticing a chill in the air but not yet realising what was gathering far above and far away. That's one of the quiet wonders of the atmosphere. It can build something enormous without making a sound, until suddenly it arrives at your doorstep in the form of snowflakes drifting past a streetlight or wind rattling a window pane. Another part of Fern's story involves the shape of the land itself. Mountains, valleys, coastlines, and plains all influence how air moves. When wind encounters a mountain range, it has to go somewhere. Often it rises, and rising air cools, which can lead to increased snowfall on the windward side of mountains. On the other side, the air descends, warming and drying, sometimes creating sharp differences in weather over relatively short distances. As Fern approached certain regions, these features helped shape where the heavier snow fell, where ice formed, and where winds accelerated. In some places, narrow bands of intense snowfall developed, while just a few miles away, conditions were calmer. It's a reminder that even within a large, powerful system, the experience of a storm can be deeply local, shaped by hills, rivers, buildings, and the exact path the system takes. Above all of this, the jet stream continued to guide Fern's movement. Its curves and dips acted like a kind of atmospheric highway, steering the storm along a particular route. When the jet stream slows down or becomes more wavy, storms can linger in one place longer than usual, dropping more snow or rain than they would if they moved quickly through. That lingering effect can turn an ordinary winter storm into something more disruptive, simply because it stays put and keeps delivering. At the same time, the Earth itself was contributing in quieter ways. The angle of sunlight in winter, the length of nights, the cooling of the land and the lingering warmth of the oceans all play into how energy moves through the system. The planet is constantly trying to balance itself, moving heat from warmer regions to cooler ones, and storms are one of the ways it does that. Fern, in this sense, wasn't just an isolated event. It was part of a much larger process, a global exchange of energy that never really stops. The storm was a visible, tangible moment in that ongoing flow, like a wave rising briefly above the surface of a much deeper, slower moving sea. As the system continued to organise, weather agencies began to take notice. Models, which are essentially complex mathematical simulations of the atmosphere, started to agree that this developing low-pressure area had the potential to become something more significant. The name Fern was assigned, and with that the storm became something people could refer to, track and talk about. Naming a storm doesn't change how it behaves, but it does change how we relate to it. It becomes a character in the story of the season, something that feels a little more personal than a string of numbers or a technical description. On the ground, the signs began to show. The air grew sharper, clouds thickened, their edges soft and heavy-looking, as if they were holding more than just water. The wind shifted, sometimes subtly, sometimes with a noticeable push. These are the small, sensory clues that something is on the way. The atmosphere's quiet way of clearing its throat before it speaks more loudly. For some, Fern would arrive as a gentle snowfall, a slow, steady descent of white that softened the edges of the world and made everything feel quieter. For others, it would bring freezing rain, coating roads and branches in a thin, glassy layer that turned familiar places into something fragile and reflective. In still other areas, the wind would be the main character, pushing snow into drifting shapes and reminding everyone that air, though invisible, can carry a surprising amount of force. But all of these experiences, different as they were, trace back to the same set of processes: the meeting of warm and cold, the rise and fall of air, the pull of pressure differences, the guiding hand of high-altitude winds. Fern was not a single cause, not a simple answer, but a web of interaction stretching from the surface of the ocean to the edge of space. What makes storms like this especially interesting is how sensitive they are to timing. If the cold air had arrived a few hours earlier or later, if the jet stream had dipped a little farther north or south, if the ocean's surface had been slightly cooler, the entire story could have played out differently. Snow might have fallen as rain, a powerful system might have weakened instead of strengthening, the path of the storm could have shifted, changing who felt its effects and who barely noticed it at all. This sensitivity is part of what makes weather so difficult to predict, perfectly, and so fascinating to watch. The atmosphere is a complex system, full of feedback loops and interconnections. Small changes can grow into large ones, and large patterns can sometimes dissolve into almost nothing. Fern was, in a way, a snapshot of that complexity. A moment when many factors lined up just enough to create something that reached into people's lives. As you listen to this, maybe you're remembering how the storm felt where you were, the sound of wind against a wall, the quiet that comes with heavy snow, the way streetlights glow differently when ice coats the air with tiny reflective surfaces. Or maybe Fern passed far from you, and you only experienced it as a series of updates, a moving shape on a map, a headline that came and went. Either way, the story of what caused it begins far beyond any single place. Fern wasn't just a storm that happened. It was a moment in a much larger conversation between Earth's surface, its atmosphere, and the energy that flows between them. So take another slow breath. Let the image of that invisible river of air circling the planet settle in your mind. Somewhere along its winding path, the conditions that shaped Fern were already forming, long before anyone knew to look for them. Rather than easing in gently, Winter and Fern's story made its presence known with a kind of confidence that was hard to ignore. One day, the air still carried the faint memory of something milder, something that felt like it might belong to late autumn rather than the heart of the cold season. Then, almost without ceremony, the temperature slipped, the wind found a sharper edge, and the sky took on that heavy, layered look that often signals a change is already underway. It wasn't a single moment that marked the shift. It was a series of small cues scattered across hours and miles that together added up to something louder than expected. Long before the first snowflake drifted down, or the first gust rattled a window, the atmosphere was already rearranging itself on a grand scale. To the north, Cold air had been gathering like a slow-moving tide, pooling over higher latitudes and land that had been losing heat night after night. Land cools faster than water, and as the days shortened and the sun's angle dropped lower in the sky, vast stretches of ground released the warmth they had stored through the warmer months. The air above them cooled, grew denser, and settled closer to the surface, building a reservoir of cold that was quiet, patient, and heavy. At the same time, far to the south or over open water, a different story was unfolding. Oceans, lakes, and even large rivers held onto their heat longer, releasing it slowly into the air above. That warmth didn't stay put. It rose, drifted, and began to meet the advancing edge of colder air. Where those two worlds touched, the atmosphere found itself in a state of imbalance, and the only thing it ever really wants is balance. The movement toward balance is what gives weather its energy. Warm air rises, cold air sinks, and the planet's rotation nudges everything into curved paths rather than straight lines. This is why storms don't simply move north to south or east to west in neat lines. They swirl, bend, and arc across maps, guided by forces that are both simple and deeply intertwined. As Fern's broader system took shape, one of the most noticeable features was how quickly the temperature changed across relatively short distances. In some places, thermometers dropped steadily over the course of a day. In others, the shift felt more abrupt, like stepping from one room into another where someone had left a window wide open. This kind of sharp temperature gradient is often a sign that a strong boundary between air masses is nearby, and boundaries like that tend to make themselves heard. The sound of winter arriving is rarely a literal one, at least not at first. It's more of a feeling, the way your breath becomes visible, the way the air seems to carry smells differently, sharper and cleaner, the way the ground feels more solid underfoot, as if it's bracing itself. But for those watching the data, listening to the quiet conversation of satellites, weather balloons, and radar scans, the arrival was loud in another way entirely. Pressure readings began to fall, winds at higher altitudes picked up speed, moisture streams became more defined, flowing toward the developing low-pressure centre that would soon be known as Fern. Each of these changes was a kind of signal flare, telling meteorologists that the system wasn't content to stay small or polite. One of the reasons this particular winter arrival felt louder than expected had to do with how different pieces of the atmosphere lined up at just the right time. A dip in the jet stream, sometimes called a trough, allowed colder air to spill farther south than it normally would. At the same time, a ridge, or a northward bulge in the jet stream elsewhere, helped lock that pattern in place for longer than usual. Instead of sliding through and moving on, the system lingered, drawing in more energy and moisture as the hours passed. When patterns stall like this, the effects on the ground can grow more pronounced. Snow has more time to fall, ice has more time to accumulate, winds have more time to shape drifts and press against structures. It's not always about how intense a storm is at any single moment. Sometimes it's about how long it stays and how steadily it keeps delivering its particular brand of weather. In Fern's case, the atmosphere seemed content to keep the door open for cold air. Behind the main system, more chilly air followed, reinforcing the wintry conditions instead of allowing a quick return to something milder. This created a sense that winter wasn't just visiting, it was settling in, rearranging the furniture, and planning to stay for a while. Another factor that added to the storm's presence was the way moisture and cold overlapped. Cold air on its own can be dry and relatively uneventful. Moisture on its own can lead to rain and clouds. But when cold air and abundant moisture meet, especially near the surface, the result often comes down as snow, sleet, or freezing rain, each with its own personality and its own way of changing the landscape. Snow tends to soften the world. It absorbs sound, blurs edges, and turns busy scenes into something quieter and simpler. Freezing rain does almost the opposite. It coats everything in a clear, glassy layer that reflects light and amplifies sound, making every footstep and every branch movement feel more noticeable. Wind adds another layer, pushing precipitation sideways, shaping it into lines and curves, and reminding everyone that air, even when cold, is rarely still. Fern managed to bring a mix of these elements to different places along its path. Some regions experienced long stretches of steady snowfall, the kind that piles up gradually and changes the colour of the world without much drama. Others dealt with more complicated conditions, where temperatures hovered right around the freezing point, turning rain into ice as soon as it touched a surface. That narrow band of temperatures is often where the most disruptive winter weather happens, not because the storm is necessarily stronger, but because the form the precipitation takes makes everyday movement more difficult. As the system moved, it also interacted with local features in ways that made its arrival feel uneven and, in some cases, surprising. Cities, for example, often experience what's called an urban heat island effect. Buildings, roads, and other structures absorb heat during the day and release it slowly at night, keeping temperatures slightly higher than in surrounding rural areas. This can mean the difference between snow and rain, or between ice that forms and ice that melts. Bodies of water play a similar role. A lake or a wide river can keep nearby air a few degrees warmer, which might spare one town from heavy snow while another, just a short drive away, ends up under a thick white blanket. When Fern passed through areas like this, the map of its impact looked patchy, almost artistic, with sharp lines separating very different experiences of the same storm. The louder-than-expected feeling also came from how people encountered the storm in their routines. A commute that usually took 20 minutes suddenly took an hour. A familiar street looked unfamiliar under a layer of snow or ice. Power lines and trees, weighed down by accumulation and pushed by wind, sometimes gave way, turning the simple act of turning on a light into something less certain. These disruptions can make a storm feel more significant, even if, in purely meteorological terms, it falls within a range that happens regularly. Weather doesn't exist in a vacuum. It exists in the context of lives, schedules, infrastructure, and expectations. When it pushes against those things, it feels louder, more present, more memorable. Behind the scenes, the energy driving Fern continued to cycle through the system. Air spiraled inward toward the low-pressure center, rose, cooled, and then spread outward at higher altitudes before sinking again farther away. This circulation pattern is one of the defining features of mid-latitude storms, and it's what gives them their broad, comma-shaped appearance on satellite images. As long as the temperature differences remained strong and the jet stream kept the system in a favourable position, that circulation could sustain itself. The storm didn't need a single dramatic trigger to keep going. It fed on the steady contrast between warm and cold, between rising and sinking air, between land and sea. What's interesting is how this contrasts with how storms are often portrayed. It's tempting to look for a single cause, a moment when something happened and the storm began. In reality, it's more like a long conversation. The atmosphere speaks in gradients, in flows, in imbalances that develop over days and weeks. Fern's louder arrival was the result of many voices in that conversation speaking at once, in the same general direction. As the storm's influence spread, the broader climate patterns in the background also played a subtle role. Large-scale oscillations in ocean temperatures and atmospheric pressure can tilt the odds towards certain types of weather in a given season. They don't create individual storms on their own, but they can make the environment more or less welcoming for systems like Fern to grow and persist. Think of it like setting a stage. The props and lighting don't write the script, but they shape how the performance unfolds. In this case, the stage included sea surface temperatures, long-term pressure patterns, and the seasonal shift of the sun's energy. Fern stepped into that setting and followed the paths that were easiest to take. For people watching from the ground, the experience of winter arriving loudly was often tied to contrast. The difference between before and after. A bare sidewalk one day, a slippery one the next. A clear sky replaced by a ceiling of clouds. A quiet night punctuated by the sound of wind or the scrape of snowplows in the distance. There's a certain rhythm to these changes, even when they feel abrupt. The atmosphere moves in cycles, not straight lines. Cold follows warm, calm follows wind. Clear skies often return after a storm passes, bringing with them a kind of stillness that feels earned. As Fern continued on its path, it left behind these small pockets of after effects. In some places, it was the sparkle of ice in the sunlight. In others, it was the soft crunch of snow underfoot. In still others, it was simply a memory, a story about how the weather surprised everyone for a day or two. What makes this part of the story important is not just that winter arrived with more force than expected, but that it showed how responsive the atmosphere can be to the right combination of factors. Fern didn't break any rules. It followed the same physical laws that govern every breeze and every cloud. But when those laws lined up in just the right way, the result felt bigger, more noticeable, more insistent. The storm's louder presence wasn't about a single extraordinary ingredient. It was about timing, positioning, and connection. About how air in one place influenced air in another. About how water stored months of sunlight and then released it at just the right moment. About how a bend in a high-altitude wind stream shaped conditions on the ground. All of these threads are still there, even now, even as Fern fades into the background and becomes part of the season's story rather than its headline. The atmosphere hasn't stopped moving. The oceans haven't stopped exchanging heat with the sky. The jet stream hasn't settled into a permanent shape. So as you listen, perhaps imagine that larger flow still in motion. Picture the cold air slowly shifting, the warm air rising somewhere far away, the winds tracing invisible paths overhead. Fern's louder arrival was just one moment in that endless movement, one chapter in a story that doesn't really pause, even when the world outside your window feels still. Sometimes the most human thing we do in the face of something vast and impersonal is give it a name. We name ships before sending them across oceans. We name mountains, rivers, and even distant stars. And when a storm begins to gather enough attention, enough presence, and enough potential to shape people's days, we give it a name too. That's how Fern stepped out of a cluster of pressure systems and temperature gradients and became something that felt, in a small way, like a character in the story of the season. A name doesn't change the physics of a storm. The air doesn't swirl differently because someone called it Fern instead of a developing low-pressure system. Snow doesn't fall more softly or more fiercely because of a word attached to it. But for the people watching, listening, and preparing, a name does something else entirely. It gives the storm a kind of identity, a shorthand that turns abstract data into something you can talk about over breakfast or mention in a message to a friend. Before Fern had a name, it was just a pattern on a map, a set of numbers on a forecast model, a cluster of clouds forming over water and land. Meteorologists could describe it in technical terms, talking about pressure drops, temperature gradients, and moisture streams. All accurate, all important, and all slightly distant from the way most people experience the world. Once it became Fern, it crossed a subtle line. It became something you could refer to directly. Fern is expected to arrive tonight. Fern might bring heavy snow to the north. Did you hear what Fern is doing over by the coast? The storm, in a way, stepped into conversation. This habit of naming storms is relatively recent in the long history of weather watching. For most of human existence, storms were simply storms. They were described by what they did or where they happened. The Great Flood, the winter of deep snow, the night the wind tore the roof away. These descriptions were rooted in experience, not in classification. The modern system of naming storms grew out of a desire for clarity and communication. When meteorologists and emergency planners talk to each other and to the public, it helps to have a simple, consistent label. A name is easier to remember than a string of coordinates or a technical designation. It reduces confusion, especially when multiple systems are active at once. In the case of winter storms, the naming process isn't as standardized or universal as it is for hurricanes. Different organizations use different criteria. Some focus on expected impacts, like the potential for widespread snowfall or ice. Others look at how large an area might be affected or how disruptive the storm could be to travel and daily life. When a system meets certain thresholds, it earns a name and, with it, a kind of spotlight. Fern's name placed it into a list, a sequence of storms that would mark the season. The names themselves are often chosen well in advance, long before anyone knows which one will be attached to which weather system. They're just words waiting for a moment to become relevant. When Fern was selected, it wasn't because the storm felt particularly Fern-like, it was simply next in line. And yet, once the name was attached, people began to associate it with their own experiences. For someone who spent the day shoveling snow, Fern might feel like a stubborn guest that overstayed its welcome. For someone who enjoyed watching flakes drift past a window, Fern might feel almost gentle, even if the wider impacts were anything but. This is one of the interesting effects of naming. It invites a kind of personalization. We start to talk about what a storm is doing, rather than what the atmosphere is doing. Fern is moving in from the west. Fern is strengthening. Fern is losing energy. The language shifts subtly towards something that sounds more like behaviour than process. There's a comfort in that, even when the situation itself isn't comfortable. Turning a complex, powerful system into something that can be named and discussed makes it feel a little more manageable. It doesn't make it safer or less disruptive, but it can make it feel less abstract, less like an unknowable force, and more like a known presence. This tendency to personify natural phenomena runs deep. We talk about angry seas, gentle rain, stubborn winds. We give storms moods and intentions, even though in reality they have neither. The atmosphere doesn't decide to be harsh or kind. It follows physical laws, responding to energy, pressure, and motion. But our minds, tuned for social interaction and storytelling, naturally frame these patterns in more human terms. Fern's name also made it easier to follow the storm's journey. As it moved across regions, news updates, weather alerts, and casual conversations could all refer to the same thing without needing to re-explain what was being discussed. The name became a thread connecting different experiences of the same system. Someone hundreds of miles away might hear about Fern and picture a storm in the abstract. Someone directly in its path might feel it as a very real presence, shaping the day's plans and the night's sounds. The name bridged those perspectives, linking the distant and the immediate. Behind that simple word, though, the storm remained what it always was, a circulation of air around a low-pressure centre, a flow of moisture being lifted, cooled, and released. A balance-seeking system in a planet that is constantly redistributing heat. The personality we gave it was layered on top of a set of physical processes that didn't notice, or care what we called them. The process of naming also plays a role in how we remember storms after they've passed. It's easier to recall the week Fern came through than that low-pressure system in late winter. Names anchor memories. They give us a handle to hold on to when we look back and try to place events in time. This can shape how storms become part of local or personal history. People might remember where they were when Fern arrived, what they were doing, who they were with. The storm becomes a marker, a point in the timeline that helps organize other memories around it. There's also an element of storytelling at work. A named storm feels like it has a beginning, a middle, and an end. It forms, it travels, it impacts, and then it fades. That arc fits neatly into the way we like to understand events, even if the reality is more continuous and less neatly packaged. In truth, Fern didn't suddenly begin when it was named, and it didn't suddenly stop when the last advisory was lifted. The atmosphere that gave rise to it kept moving, kept exchanging energy, kept evolving. The name simply marked a portion of that ongoing flow, carving out a segment that we could focus on and talk about. This focus can be useful in practical ways. It helps emergency services coordinate responses. It helps media communicate risks. It helps people decide whether to change travel plans or prepare for possible disruptions. In these contexts, a name isn't just a storytelling device, it's a tool for organisation and safety, but it also shapes the emotional tone around a storm. A named system can feel more significant, more noteworthy, even if its actual impacts are similar to other unnamed events. The attention it receives can amplify the sense of importance, making it feel like a major moment rather than part of the regular rhythm of weather. For some, this can be reassuring. It feels like the storm is being watched, tracked, and understood. For others, it can add a layer of tension, making the event feel larger or more ominous than it might otherwise. Fern, like all named storms, carried both of these possibilities. In some areas, it lived up to the attention, bringing conditions that genuinely disrupted daily life. In others, it passed more quietly, leaving behind little more than a story and a name that would soon be replaced by the next one on the list. The way people reacted to Fern often depended on their relationship with winter itself. For those who enjoy snow and cold, the storm might have felt like an opportunity. For those who find winter challenging, it might have felt like an unwelcome extension of an already difficult season. The name didn't dictate those reactions, but it gave them a common reference point. There's also a subtle cultural layer to naming. Different regions and communities have their own histories with storms, their own ways of talking about weather, their own thresholds for what feels significant. In some places, a few inches of snow is a major event. In others, it barely registers. The same named storm can be experienced very differently depending on where you are and what you're used to. Fern's personality in that sense wasn't a single, shared thing. It was a collection of impressions shaped by geography, infrastructure, and individual experience. For one person, Fern might be remembered as the day the power went out and candles were lit. For another, it might be the day a quiet walk through falling snow felt especially peaceful. The act of naming doesn't flatten these differences, but it does connect them. It ties together a patchwork of experiences under a single label, creating a sense of a shared event, even across distances. If you step back and look at this from a broader perspective, it's a small example of how humans interact with the natural world. We observe, categorize, label, and narrate. We turn processes into stories. We turn patterns into characters. It's not because the world needs us to do that, but because we do. The atmosphere doesn't require a name to function. It doesn't need an audience. It moves heat, moisture, and momentum according to physical principles that operate whether or not anyone is watching. But we, as listeners and observers, often need a way to frame what we see and feel. A name is one of the simplest tools we have for that. In the case of Fern, the name also created a sense of continuity. As updates rolled in over hours and days, the same word kept appearing, linking each new piece of information to the last. The storm became a thread running through the forecast, through conversations, through the quiet moments when people checked the weather on their phones before stepping outside. That continuity can make a storm feel like a presence that accompanies you for a while, rather than a series of disconnected weather events. You're not just experiencing snow one day and wind the next. You're experiencing Fern unfolding over time. This unfolding mirrors, in a small way, the actual life cycle of the storm. It forms, grows, reaches a peak, and then gradually weakens as it moves into an environment that can no longer support it. The name stays with it through all of these phases, even as the underlying system changes. At some point, Fern's low-pressure centre filled in. The temperature contrast softened, the jet stream shifted. The circulation that had kept the storm organised began to lose its structure. The clouds thinned, the precipitation tapered off, and the winds eased. On the ground, the signs of the storm lingered longer than the storm itself, in the form of snowbanks, icy patches, or just a different feel to the air. The name too lingered, at least for a while. People referred back to it. After Fern, things really cooled down. Before Fern, the roads were clear. It became a marker, a point of reference in the ongoing flow of the season. Eventually, though, even the name faded. Another storm took its place in the forecasts. Another word stepped into the spotlight. Fern became part of the background, a memory rather than a presence. What remains interesting is not just what the storm did, but what the act of naming reveals about us. It shows how we seek connection with the systems that shape our lives, even when those systems operate on scales and in ways that are far beyond our direct control. We give a storm a name, and in doing so, we bring it a little closer, make it a little more familiar. We turn a vast, complex pattern of air and energy into something we can talk about, remember, and share. On one level, Fern is a set of physical processes governed by temperature, pressure, and motion. On another, Fern is a word, a label, a point in a human narrative about a winter that arrived loudly and left its mark. Both of these layers are real in their own ways. The physics shapes the world outside your window. The story shapes how you think about what you see there. And somewhere between those two layers, between the swirling of air and the quiet conversations that follow it, the storm finds its place in memory, not just as a weather event, but as a small chapter in the ongoing dialogue between people and the planet they live on. Movement in the atmosphere rarely announces itself. There's no sound when a mass of cold air begins to slide across a continent, no visible line in the sky marking where one temperature ends and another begins. And yet, this quiet shifting of invisible pieces is one of the most important parts of how storms like Fern take shape. Cold air doesn't just appear in a place, it travels, guided by the contours of the planet, the pull of gravity, and the restless flow of winds that never truly stop. To understand how cold air moves, it helps to think about its basic nature. Cold air is denser than warm air. The molecules inside it are packed a little closer together, moving more slowly, carrying less energy. Because of that, cold air tends to stay closer to the surface of the Earth, spreading out like a slow, heavy liquid rather than rising upward. Warm air, lighter and more energetic, does the opposite. It climbs, expanding as it goes, making room for other air to move in beneath it. This simple difference creates a kind of ongoing exchange. Warm air rises, cold air flows in to replace it. The planet's rotation adds a twist, quite literally, bending these flows into curved paths rather than straight lines. The result is a constantly shifting pattern of air masses, each with its own temperature, moisture content and history. Cold air often begins its journey in places where sunlight is scarce for long stretches of the year. High latitudes, snow-covered land, and long winter nights allow the ground to lose heat steadily. The air in contact with that ground cools down as well, growing heavier and more stable. Over time, this can create large reservoirs of cold air, sometimes referred to as cold pools, that sit quietly over regions like northern plains, frozen forests, or polar landscapes. These cold pools don't stay put forever. They're held in place by surrounding winds and pressure patterns, but when those patterns change, the cold air can begin to move. It doesn't rush forward like a gust. Instead, it spreads, oozing outward along the surface, following the lowest paths available, slipping into valleys, across plains, and around obstacles. One of the main drivers of this movement is pressure. Areas of high pressure often form over cold regions because cold, dense air tends to sink, increasing the weight of the air column above a given spot. This creates a dome of higher pressure at the surface. Around that dome, air naturally wants to flow away, moving toward areas of lower pressure where air is rising and the surface pressure is lower. As cold air flows outward from a high-pressure area, it can travel hundreds or even thousands of miles, especially if the larger-scale wind patterns support that motion. Along the way, it may pick up moisture, lose some of its chill, or become modified by the surfaces it passes over, but its basic character often remains recognizable. In Fern's case, part of the story involved a significant push of cold air moving out of its source region and into areas that were not quite as cold to begin with. This created a sharp contrast, a boundary where two very different types of air met. That boundary is what meteorologists call a front. A cold front forms when a mass of cold air advances into a region of warmer air. Because the cold air is heavier, it wedges itself underneath the warmer air, lifting it upward. This lifting is a powerful mechanism for creating clouds and precipitation, because as the warm air rises, it cools and its moisture begins to condense. The movement of a cold front is often experienced on the ground as a noticeable shift. The wind direction might change, the temperature can drop quickly, the sky might transform from a uniform layer of clouds to towering textured formations. Even the smell of the air can feel different, crisper and cleaner after the front passes. But these front lines are rarely straight or simple. They curve, bend, and sometimes break into smaller segments. Their shape and speed are influenced by the winds higher up in the atmosphere, especially those flowing along the jet stream. The jet stream plays a key role in guiding cold air. When it dips southward, it opens a pathway for colder air to follow. When it arches northward, it can act like a barrier, keeping cold air bottled up in its source region. These dips and bulges, often called troughs and ridges, can persist for days or shift rapidly, depending on the broader atmospheric pattern. During the period when Fern was developing, the jet stream took on a shape that favoured the southward movement of cold air. A trough allowed colder air to spill into lower latitudes, setting the stage for the kind of temperature contrasts that give storms their energy. As this cold air advanced, it didn't move as a uniform block. The surface of the Earth is uneven, and that unevenness shapes how air flows. Mountains can act as walls, forcing air to rise and spill over, sometimes creating strong winds on the downwind side. Valleys can channel cold air, guiding it along narrow paths and allowing it to pool in low-lying areas. This is why, on a cold morning, you might find frost in a valley while a nearby hill remains clear. Cold air settles into the lower spots, like water finding the bottom of a bowl. During a larger scale movement, the same principle applies, just on a much bigger canvas. Bodies of water also influence the journey of cold air. When cold air passes over a relatively warm lake or ocean, it can pick up heat and moisture from the surface below. This process can destabilize the air, making it more likely to rise and form clouds. In some regions, this leads to lake-effect snow, where narrow bands of heavy snowfall form downwind of large lakes as cold air sweeps across them. Even when the moisture doesn't fall immediately, the added energy can help sustain or intensify a nearby storm system. In Fern's case, moisture from open water played a role in feeding the clouds and precipitation that accompanied the storm's passage. Another aspect of cold air movement that often goes unnoticed is how layered the atmosphere is. The air near the surface can be doing something quite different from the air a mile or two above. Cold air might be sliding in at ground level, while warmer air flows overhead in the opposite direction. This layering can create what's known as an inversion, where a layer of warm air sits above a layer of cold air, trapping it in place. Inversions can keep cold air pooled in a region, prolonging wintry conditions even when the broader pattern suggests things should be warming up. In storm situations, these layers can also determine what kind of precipitation falls. If warm air flows over a shallow layer of cold air near the surface, snowflakes can melt into raindrops on the way down, and then refreeze as they pass back through the cold layer, creating sleet or freezing rain. These subtle vertical temperature differences can have a big impact on what people experience on the ground. As Fern's system moved, it encountered a variety of these layered conditions. In some areas, the cold air was deep and well established, allowing snow to fall all the way to the surface. In others, a thin layer of cold air sat beneath warmer air, setting up the conditions for ice. The shifting of cold air is also influenced by the time of day. At night, the ground cools more rapidly, chilling the air just above it. This can strengthen cold pools and make the air even denser and more stable. During the day, sunlight can warm the surface, mixing the air and sometimes eroding the cold layer from below. These daily cycles add another layer of complexity to how a storm evolves. A system that passes through an area at night might encounter colder, more stable air than it would during the day, changing the balance between snow and rain, or between calm and wind. All of this movement happens within a larger planet-wide circulation. The Earth is constantly redistributing heat from the equator toward the poles and cold from the poles toward the equator. Storms like Fern are part of that redistribution, acting as vehicles for moving energy across vast distances. Cold air flowing southward and warm air flowing northward meet, mix, and exchange energy. The atmosphere doesn't achieve a permanent balance, but it's always working toward one, and the process of trying is what keeps weather in motion. There's something quietly fascinating about how slow and how fast this can be at the same time. The large-scale patterns that guide cold air can take days or weeks to shift, but the effects on the ground can feel immediate. A change in wind direction, a sudden drop in temperature, a new texture to the clouds overhead. These small sensory changes are the local expressions of a much bigger story, one that spans continents and oceans. When you feel a cold wind on your face, you're not just feeling the air from a few feet away. You're often feeling air that has travelled hundreds of miles, carrying with it the imprint of the surfaces it passed over and the conditions it came from. In Fern's case, the movement of cold air was one of the threads that tied together distant regions. A reservoir of chill in one part of the world influenced the weather in another, connected by the flowing pathways of the atmosphere. What makes this especially interesting is how these pathways can shift from year to year, or even from week to week. Some winters are marked by strong, steady flows of cold air into certain regions. Others keep the cold bottled up farther north, allowing milder conditions to dominate. These variations are influenced by patterns in the ocean and atmosphere that operate on longer timescales. Oscillations in sea surface temperatures, changes in pressure patterns, and even variations in solar energy can tilt the balance one way or another. They don't determine the exact path of every cold front, but they shape the background conditions in which those fronts form and move. As Fern unfolded, it did so within one of these broader patterns, taking advantage of a window where the atmosphere was more open to southward cold air movement. The result was a system that felt in many places sharper and more wintry than what had come before. It's also worth noting that cold air doesn't always arrive in a single clean sweep. Often, it comes in waves. One push brings a drop in temperature. Another follows a day or two later, reinforcing the chill. This staggered arrival can make winter feel like it's knocking repeatedly, each time a little more firmly. Fern was part of such a sequence. The initial movement of cold air set the stage, but additional surges helped maintain the conditions that allowed the storm's effects to linger. Even after the main system moved on, the air behind it remained cold enough to keep snow and ice from melting quickly. From a distance, this can look like a single event. From within it, it often feels like a series of changes, each one connected to the last, each one part of a larger flow. As you picture all of this, you might imagine the atmosphere as a vast, slow-moving mosaic. Each piece of air has its own temperature, its own moisture, its own path. The edges between these pieces are where much of the action happens, where clouds form, where storms grow, where weather becomes something you can see and feel. Fern's story at this stage is very much about those edges, about how a mass of cold air met something warmer, about how that meeting created motion, lift, and energy, about how the planet's rotation and shape guided that energy along certain routes instead of others. And even as we talk about it in these broad terms, the details remain incredibly specific. A bend in the jet stream here, a mountain range there, a patch of open water somewhere else. Each one nudges the flow, subtly changing the outcome. The atmosphere doesn't move pieces on a board. It flows continuously, responding to everything it touches. Fern emerged from that flow shaped by it and carried along by it. High above the clouds, far beyond the reach of snowfall and streetlights, there is a current of air that rarely enters everyday conversation, yet quietly shapes nearly every weather story that unfolds below. It doesn't have a surface you can see or a sound you can hear, but its influence can stretch across continents. This is the jet stream, and in Fern's case it didn't take a straight path. It wandered, curved, and lingered in ways that gave the storm both time and opportunity to grow. To picture the jet stream, it helps to imagine the atmosphere not as a uniform blanket of air, but as a layered system, with different speeds and temperatures stacked on top of one another. Near the surface, winds can be gentle or gusty, slow or fast, shaped by hills, buildings and forests. Higher up, several miles above the ground, the air is thinner, colder, and often moving much more quickly. This is where the jet stream lives, a narrow band of strong winds that can reach speeds well over 100 miles per hour. The reason it exists at all comes back to the same theme that runs through much of Fern's story, the contrast between warm and cold. The Earth is heated unevenly. The equator receives more direct sunlight than the poles, which means the air there tends to be warmer. As you move toward higher latitudes, the sunlight is weaker and the air becomes cooler. Where these different air masses meet, especially at higher altitudes, the temperature difference creates a strong pressure gradient, and air begins to move rapidly along that boundary. The result is the jet stream, flowing from west to east, circling the planet like a restless ribbon. In an idealized world, this ribbon might form a smooth, nearly straight line around the globe, but the Earth is not idealized, and neither is its atmosphere. Continents, oceans, mountain ranges, and the rotation of the planet itself all introduce irregularities. The jet stream responds by developing waves, dips, and bulges, turning its path into something more like a winding river than a perfect circle. These waves are often described in terms of ridges and troughs. A ridge is a northward bulge in the jet stream, where warmer air pushes farther toward the poles. A trough is a southward dip, where colder air plunges toward lower latitudes. Together, they create a pattern that can move across the map, shifting weather as it goes. In the period leading up to Fern, the jet stream developed a particularly pronounced trough. Instead of flowing in a relatively tight, fast-moving path, it sagged southward, creating a kind of atmospheric valley. This detour opened the door for cold air to move more freely into regions that might otherwise have stayed milder. At the same time, it created a favourable environment for low-pressure systems to form and deepen along the boundary between warm and cold air. One of the key things about these large waves in the jet stream is that they can slow down the overall movement of weather systems. When the jet stream is relatively straight and fast, storms tend to move quickly from west to east, passing through an area in a day or two. When the jet stream becomes more wavy, with deep troughs and tall ridges, those systems can stall or creep along more slowly. Fern benefited from this slower pace. Instead of being swept along and pushed out of the way, it found itself in a region where the upper-level winds were more supportive of development than of departure. The jet stream above provided a kind of ventilation, allowing air to rise more easily from the surface and spread out at higher altitudes. This helped keep the surface pressure low, which in turn encouraged more air to flow inward and upward, feeding the storm. This relationship between the jet stream and surface storms is one of the most important links in the chain of weather. At the surface, a low-pressure system draws air in. For that air to keep rising, it has to go somewhere when it reaches higher levels of the atmosphere. If the jet stream is positioned in a way that helps pull that air away, it creates space for more air to rise from below. The storm can maintain or even increase its strength. If the jet stream is positioned poorly, the rising air can pile up aloft, making it harder for the system to sustain itself. In Fern's case, the upper-level winds were arranged in a way that favoured this kind of outflow. It's a bit like having a chimney for the storm. As long as air can escape at the top, more can be drawn in at the bottom. The shape of the jet stream also helped define where Fern could go. Storms tend to follow the flow of the winds above them, much like leaves carried along by a river. When the jet stream curves, the storms curve with it. This is why weather maps often show systems following arsing paths rather than straight lines. As the jet stream dipped and rose, it guided Fern along a route that brought it into contact with both cold and warm air, allowing the storm to keep drawing energy from the temperature contrast. Had the jet stream taken a more direct path, Fern might have been steered away from those contrasts and weakened more quickly. Another aspect of the jet stream's detour was how it interacted with other large-scale features in the atmosphere. High-pressure systems, which are often associated with calmer weather, can act like obstacles in the flow. When a strong high-pressure area sets up, the jet stream may be forced to bend around it, deepening troughs and amplifying ridges elsewhere. During Fern's development, such a blocking pattern played a role. A region of relatively stable, high-pressure air in one part of the hemisphere helped lock the jet stream into a more exaggerated wave pattern. Instead of smoothing out, the bends in the flow became more pronounced and longer-lasting. This kind of blocking can have wide-reaching effects. It can lead to prolonged periods of certain weather types in specific regions. Cold can linger where the trough sits. Warm, dry conditions can persist under a ridge. Storms can repeatedly follow similar paths, one after another, like trains on a track. For people on the ground, this can translate into a sense that the weather is stuck. Days of similar conditions, repeated rounds of snow or rain, little relief in between. Fern was part of a pattern like this, not just an isolated event, but a participant in a broader arrangement of atmospheric traffic. The jet stream's detour also affected how moisture was transported. Warm air from lower latitudes often carries more water vapour. When the jet stream bends in a way that allows that air to be drawn northward and then lifted, it can provide storms with a steady supply of moisture. This is one reason why some winter storms can produce heavy precipitation, even in cold conditions. The cold determines the form of the precipitation, but the moisture often comes from much farther away. In Fern's story, moisture streams traced long paths, sometimes originating over open water hundreds or thousands of miles to the south or west. The jet stream helped guide these streams into the storm's circulation where the air was lifted, cooled, and turned into clouds and snow. It's fascinating to consider how much of what falls from the sky in one place began its journey in another. A snowflake landing on a quiet street might contain water that evaporated from an ocean far away, carried by winds high and low, and transformed along the way by changes in temperature and pressure. The jet stream, in this sense, is a kind of global conveyor belt. It doesn't just move air, it moves heat, moisture, and momentum, redistributing them around the planet. Storms like Fern are part of that redistribution, acting as nodes where these different streams come together and interact. Another subtle effect of the jet stream's shape is how it influences temperature patterns at the surface. Under a trough, where the jet stream dips southward, colder air tends to dominate. Under a ridge, where it arches northward, warmer air often prevails. This can create sharp contrasts over relatively short distances, especially when the pattern is strong and persistent. During Fern's passage, such contrasts were evident in how different regions experienced the storm. Some areas stayed firmly in the cold sector, seeing snow and ice. Others, closer to the warmer side of the boundary, experienced rain or mixed precipitation. The dividing line between these experiences often followed the contours of the upper-level flow. The jet stream also has a seasonal rhythm. It tends to be stronger and more variable in winter, when the temperature difference between the equator and the poles is greatest. This increased energy makes the flow more dynamic, more prone to developing large waves. That's one reason why winter weather can be so changeable, with rapid shifts between cold and mild, calm and stormy. Fern's development took place within this energetic winter context. The jet stream had plenty of contrast to work with, and its detour reflected that energy. The large-scale pattern was primed for movement, for exchanges between different air masses, and for the kind of atmospheric conversations that lead to notable storms. There is also an ongoing scientific discussion about how the jet stream might be changing over longer timescales. Some research suggests that warming in the Arctic is reducing the temperature contrast between the poles and the equator, which could, in some cases, lead to a weaker, more meandering jet stream. A slower, wavier flow could mean more frequent or longer-lasting weather patterns, including prolonged cold spells or extended periods of stormy weather. This is an area of active study, and the details are complex. The atmosphere is influenced by many factors, and separating long-term trends from natural variability is not simple. Still, the idea that changes in the planet's overall energy balance could influence the behaviour of this high-altitude wind adds another layer to the story of storms like Fern. Whether or not Fern itself was influenced by these broader trends is difficult to say with certainty. Individual storms are shaped by immediate conditions, by the specific configuration of the atmosphere at a given moment, but they unfold within a larger system that is itself evolving over time. For someone standing outside in the cold, feeling the wind push past, it's easy to forget that part of that experience is being shaped by air moving miles above their head, following a path that curves around the planet. The connection between the quiet, high-altitude flow and the very tangible conditions on the ground is one of the most striking aspects of weather. It's also one of the reasons why predicting storms is such a challenge. Small changes in the position or strength of the jet stream can lead to significant differences in where a storm goes and how strong it becomes. A shift of a few dozen miles in a trough or ridge can change which towns see snow and which see rain, which regions experience strong winds and which remain relatively calm. This sensitivity means that forecasts often involve a range of possibilities, especially several days out. Models run different scenarios, adjusting initial conditions slightly to see how the atmosphere might respond. When those scenarios begin to converge, confidence increases. When they diverge, it's a sign that the system is balanced on a kind of knife's edge, where small influences can tip the outcome one way or another. In the days leading up to Fern, this process played out in the background. Different model runs explored different paths, some showing a stronger, slower-moving system, others a quicker, weaker one. As the jet stream's detour became clearer and more established, the range of possibilities narrowed, and the storm's likely impact came into sharper focus. This process, too, is part of the story. The storm isn't just a physical event, it's also a forecast, a set of probabilities, a topic of discussion among scientists and the public alike. The jet stream's behaviour is one of the key pieces they watch, because it often holds the clue to what will happen next. As Fern moved along its guided path, the jet stream continued to evolve. Troughs shifted, ridges built and weakened. The storm responded, gradually losing the upper-level support that had helped sustain it. Without that support, the surface circulation began to fill in. The pressure rose, the winds eased, the precipitation tapered off. In this way, the jet stream didn't just help create Fern, it also helped bring its story to a close. By changing shape and position, it altered the environment in which the storm existed, making it harder for the system to maintain itself. What remains after such a system passes is often a sense of calm, a clearing of the sky, and a different pattern setting up in the atmosphere. The jet stream doesn't stop moving, it continues to trace its winding path, preparing the stage for whatever comes next. As you consider this, it's worth pausing on how much of what we experience in weather is shaped by things we never directly see. The clouds overhead are visible. The snow on the ground is tangible. The wind on your face is unmistakable. But the high-altitude currents guiding all of this remain out of sight, known mostly through instruments, models, and the patterns they leave behind. Fern's journey was, in many ways, a collaboration between the surface and the sky above it, between cold air flowing along the ground and fast-moving winds far overhead. The jet stream's long, winding detour was a crucial part of that collaboration, steering the storm, feeding it, and eventually letting it fade. And even now, as that particular path has shifted and smoothed out, the larger flow continues. Somewhere, another bend is forming, another trough is deepening, another ridge is building. The atmosphere is always in motion, always finding new ways to rearrange its pieces. Beneath the shifting winds and wandering paths of the jet stream, there is another presence that rarely gets the same attention, even though it quietly shapes nearly every storm that passes overhead. The oceans, vast, dark, and patient, They cover most of the planet, absorbing sunlight day after day, season after season, and storing that energy in their depths. They don't release it quickly or dramatically. They let it go slowly, steadily, like a long-held breath. And when cold air moves across that stored warmth, the atmosphere begins to stir. It can be easy to think of storms as something that happens in the sky alone, as if clouds and wind exist in their own separate world. In reality, much of what happens above is rooted in what happens below. The surface of the Earth, especially the surface of the oceans, is one of the main sources of energy for the atmosphere. Fern's story, like so many winter storms, was shaped by this quiet exchange between water and air. Water has a special relationship with heat. It can absorb a large amount of energy without changing temperature very much, and it can hold on to that energy longer than land can. This is why coastal areas often experience milder winters and cooler summers compared to inland regions. The ocean acts as a kind of thermal buffer, smoothing out the extremes. But this buffering doesn't mean the ocean is passive. It's constantly giving and taking, releasing heat into the air when the air is colder, and absorbing heat when the air is warmer. This exchange is one of the fundamental drivers of weather, and in winter it becomes especially important. As cold air masses move off land and over open water, they encounter a surface that is often significantly warmer than the air above it. The ocean responds by transferring heat upward. This happens in a few ways. Some of the heat moves directly, warming the air through contact. Some of it goes into evaporating water, turning liquid into vapour. That water vapour then rises, carrying energy with it into the atmosphere. This rising, warm, moist air is less dense than the colder air around it, so it continues to climb. As it does, it cools, and the water vapour it carries begins to condense into tiny droplets or ice crystals, forming clouds. In this way, the ocean doesn't just warm the air, it helps build the very clouds that later release snow and rain. For Fern, these processes were part of the background hum of energy that kept the system active. Moisture drawn from relatively warm waters was carried into the storm circulation, lifted by the rising air at its centre, and transformed into the precipitation that fell across its path. What makes this especially interesting is how far that moisture can travel. A snowflake landing on a quiet street might contain water that evaporated from an ocean surface hundreds or even thousands of miles away. The journey from sea to sky to land can take days, guided by winds at different levels of the atmosphere, shaped by pressure systems and temperature contrasts along the way. This long-distance connection is one of the reasons storms can feel so interconnected with the wider world. A change in ocean temperatures in one region can influence weather patterns far beyond its shores, altering the flow of air and moisture on a global scale. The ocean's role in Fern's story wasn't limited to providing moisture. It also helped shape the imbalance that gave the storm its energy. Storms thrive on differences in temperature, in pressure, in moisture. The greater the contrast, the more energy is available for the atmosphere to work with. In winter, one of the strongest contrasts often exists between cold, dry air over land and warmer, moist air over water. When these two meet, the atmosphere finds itself with a lot of potential energy, much like a stretched spring. The release of that energy can take the form of rising air, strengthening winds, and deepening pressure systems. As Fern developed, the presence of relatively warm water along part of its path helped maintain this contrast. Cold air flowing over that water picked up heat and moisture, becoming less dense and more buoyant. This encouraged more upward motion in the atmosphere, which in turn supported the low-pressure centre of the storm. This process can create a feedback loop. Rising air lowers the pressure at the surface. Lower pressure draws in more air from the surroundings. Some of that incoming air passes over warm water, picking up even more heat and moisture. That air then rises, further lowering the pressure. The cycle continues, as long as the environment around the storm remains favourable. The term restless air captures this sense of motion and exchange. The atmosphere above warm water in winter is rarely still. Even when the surface winds are light, there is often a steady transfer of energy happening just above the waves. Tiny eddies and currents of air form and dissolve, carrying heat upward and outward. On larger scales, these small motions combine into broader patterns. Bands of clouds form downwind of warm water, sometimes stretching for miles. Narrow corridors of heavy snow can develop when cold air passes over a lake or sea, a phenomenon known as lake effect or sea effect snow. These bands can be remarkably focused, delivering intense snowfall to one area while leaving nearby regions relatively untouched. While Fern was not solely a lake effect system, similar principles were at work. Moisture from open water fed into the storm's larger circulation, contributing to the clouds and precipitation that defined its presence. The idea of a brewing imbalance speaks to the way storms emerge from these contrasts. The atmosphere is always trying to even things out, to move heat from where there is more of it to where there is less. Storms are one of the main ways it does this. They act like mixing mechanisms, stirring warm and cold air together, redistributing energy across regions. In Fern's case, the imbalance between cold continental air and warmer maritime air created a kind of atmospheric tension. The storm became a way for the system to release that tension, to move heat and moisture from one place to another. This perspective can make storms feel less like intruders and more like participants in a larger ongoing process. They are not exceptions to the way the atmosphere works. They are expressions of it. The ocean's influence also extends beyond the immediate exchange of heat and moisture. Large-scale patterns in sea surface temperatures can shape the behaviour of the atmosphere over months or even years. Phenomena like El Niño and La Niña, which involve changes in ocean temperatures across the tropical Pacific, can alter wind patterns and pressure systems around the world. These patterns don't dictate the path of individual storms, but they can tilt the odds. They can make certain regions more likely to experience wetter or drier conditions, warmer or colder seasons, more or fewer storms. In the season when Fern formed, the background state of the oceans and atmosphere played a role in setting the stage. The broader pattern of sea surface temperatures influenced where the jet stream tended to flow, how strong certain pressure systems were, and how readily moisture was available to be drawn into developing storms. This layering of influences is part of what makes weather and climate such a complex and fascinating system. There is the immediate local interaction between air and water happening moment by moment, and then there are the slower, broader patterns unfolding over vast distances and long periods of time, shaping the context in which those moment-to-moment interactions occur. The restless air above warm oceans in winter can also be seen in the structure of clouds. When warm, moist air rises, it can form tall, layered cloud systems that stretch high into the atmosphere. These clouds often have a characteristic look on satellite images, with sweeping arms and dense cores, reflecting the organised circulation of the storm below. For Fern, these cloud patterns were a visible sign of the energy being transferred from the surface to the sky. The storm's shape was, in a way, a map of where heat and moisture were moving, where air was rising, and where it was spreading out and sinking again. Another subtle but important factor is the role of evaporation and condensation in moving energy. When water evaporates, it absorbs heat from its surroundings. When that water vapour later condenses into liquid droplets or ice crystals, it releases that heat back into the atmosphere. This release of what's known as latent heat can warm the surrounding air, making it more buoyant and encouraging further rising motion. In a developing storm, this process can add a significant amount of energy to the system. It's one of the reasons why storms with abundant moisture can intensify more quickly than those in drier environments. As Fern drew in moist air from over warm water, the condensation of that moisture within its clouds helped fuel the upward motion at its core. This didn't just produce precipitation, it also influenced the pressure and wind patterns within the storm, helping maintain its circulation. The ocean, in this sense, was not just a passive source of water, It was an active participant in the storm's dynamics, contributing energy at multiple stages of the process. It's also worth considering how the seasonal cycle shapes this interaction. In late autumn and early winter, the ocean often retains much of the heat it absorbed during the summer. The air above it, however, can cool rapidly as the sun's angle decreases and nights grow longer. This creates a particularly strong contrast between water and air, making the exchange of heat and moisture more intense. This seasonal timing can make early winter storms especially potent in terms of moisture supply. Even if the air is cold enough for snow, the underlying water can still provide the energy needed to build large active cloud systems. As winter progresses and the ocean's surface gradually cools, this contrast can weaken, changing the character of storms that form later in the season. Fern's development took place during a period when this contrast was still quite pronounced, adding to the system's ability to gather and sustain energy. The brewing imbalance also extended beyond just temperature and moisture. Pressure patterns over the ocean can influence how air flows toward or away from developing storms. A strong high-pressure system over water can direct winds along certain paths, steering moisture toward a low-pressure area farther inland. Alternatively, a low-pressure area over the ocean can draw air away from land, altering the supply of cold air feeding into a system. In Fern's case, the arrangement of pressure systems helped create a corridor through which moist air could flow into the storm's circulation. This corridor acted like an invisible channel, guiding energy and water vapor along a specific route. This kind of channeling is another example of how the atmosphere organizes itself. It doesn't move air randomly. It tends to create pathways, shaped by the distribution of pressure and the constraints of geography. As you follow these ideas, it can be helpful to imagine the planet as a constantly shifting pattern of exchanges. Heat moving from water to air moving from high pressure to low, moisture evaporating, rising, condensing and falling again. Each part of the system influences the others, creating a network of feedbacks that can either amplify or dampen a developing storm. Fern emerged at a point where several of these feedbacks were aligned in a way that favoured growth. Warm water provided moisture and energy. Cold air provided contrast. The jet stream provided guidance and upper-level support. Pressure patterns created pathways for air to move. None of these elements alone would have produced the storm as it was experienced. It was the combination, the way they overlapped in time and space, that created the particular shape and strength of Fern. From the perspective of someone standing on the ground, this complexity is mostly hidden. What's felt is the end result: the wind, the snow, the cold. But behind those sensations is a story that stretches across oceans and into the upper reaches of the atmosphere. There's something quietly humbling about that. A flake of snow landing on a sleeve can be traced back through a chain of events involving sunlight absorbed by water months earlier, heat transferred to air, winds guided by the rotation of the planet, and clouds formed miles above the surface. The simple and the vast are connected in ways that are easy to overlook. As Fern continued its journey, the ocean's role didn't end at the point of moisture supply. The storm itself, by redistributing heat and cold, altered the environment for whatever followed. Cold air moving over water can cool the surface slightly. Warm air moving over land can moderate temperatures there. Each storm leaves a subtle imprint, changing the starting conditions for the next one. This ongoing cycle means that weather is not just a series of independent events, it's a continuous process, with each system influencing what comes after it. The restless air above warm oceans is a key part of that continuity. It's a reminder that the surface of the planet and the atmosphere above it are in constant conversation, exchanging energy in a way that never truly pauses. For now, it's enough to hold onto the image of the ocean, quietly releasing its stored warmth into the passing air, and the sky above, responding with motion and cloud and change. Fern was one moment in that endless exchange, a visible ripple in a system that stretches from the depths of the sea to the edge of space, always moving, always adjusting, always finding new ways to balance itself. There is a quiet contest happening in the atmosphere at almost every moment, a kind of invisible tug of war that doesn't use ropes or hands, but weight and lift, sinking air and rising air. This contest is played out through pressure systems, and for storms like Fern, the way these systems push and pull against each other can make the difference between a modest weather event and something that leaves a lasting impression on the landscape and on memory. Air has weight, even though we rarely think about it that way. The column of air above any given point presses down on the surface below, and that pressure can be measured. When the air in that column is colder and denser, it weighs more, and the pressure at the surface is higher. When the air is warmer and rising, the column weighs less, and the pressure at the surface is lower. This simple relationship between temperature, motion, and pressure is one of the fundamental drivers of weather. High-pressure systems are areas where the air is generally sinking. As it sinks, it warms slightly and tends to dry out, making clouds less likely to form. This is why high pressure is often associated with clearer skies and calmer conditions. Low-pressure systems, on the other hand, are areas where air is rising. As it rises, it cools, and the moisture it carries can condense into clouds and precipitation. This is why low pressure is so often linked to storms. The tug-of-war comes from the fact that air naturally wants to move from areas of higher pressure to areas of lower pressure. This movement is what we experience as wind. The stronger the difference in pressure between two areas, the stronger the wind tends to be. For Fern, the atmosphere set up a situation where a strong high-pressure system in one region and a developing low-pressure system in another created a pronounced pressure gradient between them. This gradient acted like a stretched elastic band, pulling air along its length and feeding the storm with a steady flow. On one side of this arrangement, cold, dense air settled under a high-pressure dome. This dome wasn't a solid structure, of course, but it functioned like a broad, heavy presence, pressing down on the surface and encouraging the air to spread outward. On the other side, the low-pressure system that would become Fern was encouraging air to rise, drawing in surrounding air to replace what was lifting away. Between these two, the atmosphere found a pathway. Air flowed from the high-pressure area toward the low-pressure centre, accelerating as it went. This flow didn't travel in a straight line, though. The rotation of the Earth caused the moving air to curve, a result of what's known as the Coriolis effect. In the northern hemisphere, this causes winds to bend to the right of their path, leading to the familiar counterclockwise circulation around low-pressure systems and clockwise circulation around high-pressure systems. This curved motion is what gives storms their spiral shape when seen from above. It's also what creates the sense of a system rotating, even though what's really happening is air constantly moving inward, rising, and then spreading out again aloft. The positioning of the high and low pressure systems around Fern created a kind of corridor of flow. Cold air from the high pressure side streamed toward the low pressure centre, while warmer, moister air from another direction did the same. The storm sat at the meeting point of these flows, like a knot in a set of moving threads. What made this tug-of-war particularly effective was how persistent it was. The high-pressure system didn't quickly move away, and the low-pressure system didn't quickly fill in. Instead, both lingered long enough for the pressure gradient between them to remain strong for an extended period. This persistence meant that the winds feeding into Fern stayed steady. The storm didn't just get a brief surge of energy. It received a continuous supply, allowing it to maintain its structure and its impacts over time. High-pressure systems often get less attention than storms because they tend to bring quieter weather. But in situations like this, their role can be just as important. A strong, well-placed high-pressure area can act like a pump, pushing air toward a developing low-pressure system and helping it grow. In Fern's case, the high-pressure system was associated with a large reservoir of cold air. This air flowed outward along the surface, guided by the shape of the land and the broader wind patterns. As it reached the vicinity of the low-pressure centre, it joined the storm's circulation, helping define the cold side of the system. At the same time, Another high-pressure area in a different region helped guide warmer air toward the storm from another direction. The result was a convergence of air masses with very different characteristics. Cold, dry air from one side, warm, moist air from another. The low-pressure system sat in between, lifting and mixing these flows. This convergence is a key part of how storms intensify. When air flows inward from multiple directions, it has to go somewhere. At the surface, it piles up. The only available path is upward. As the air rises, it cools, clouds form, and precipitation develops. The rising motion also helps keep the surface pressure low, reinforcing the cycle. This is another example of feedback in the atmosphere. Low pressure draws in air. The incoming air rises. Rising air maintains or lowers the pressure further. The cycle continues, as long as the surrounding environment supports it. The tug-of-war between pressure systems doesn't always lead to dramatic storms. Sometimes, a high-pressure system simply dominates, keeping conditions stable for days. Other times, a low-pressure system moves through quickly, barely making an impression before it's pushed aside. What made Fern's situation notable was how balanced, and yet how tense the arrangement was. Neither the high nor the low pressure quickly won. Instead, they held each other in place for a time, maintaining a strong gradient and a steady flow of energy. This kind of balance can be delicate. Small changes can tip it one way or another. A shift in the jet stream overhead, a change in temperature at the surface, a new high-pressure system building in from the west or east. Any of these can weaken the gradient, slow the winds, and allow a storm to fade. During Fern's active period, though, the larger pattern remained supportive. The high-pressure areas stayed put. The low-pressure centre remained well-defined. The atmosphere kept pulling on both ends of the rope, so to speak. The shape of the land also played a role in how this tug-of-war was experienced on the ground. Mountains can enhance pressure differences locally by blocking or channeling air. When wind is forced through a narrow gap or over a ridge, it can accelerate, much like water flowing through a narrowing river channel. In some regions affected by Fern, this led to stronger winds than might have been expected based solely on the storm's central pressure. Valleys and passes became wind corridors, amplifying the sense of the atmosphere being pulled tight between competing pressure systems. Another aspect of this contest is how pressure systems evolve over time. A high-pressure system can weaken as the air within it warms or mixes with surrounding air. A low-pressure system can fill in as the rising air aloft is no longer removed efficiently by upper-level winds. Fern's low-pressure centre went through phases. At times, it deepened, meaning the pressure at its core dropped further, strengthening the winds and the circulation. At other times, it began to fill in, a sign that the storm was losing some of its support. These changes often occurred in response to what was happening higher up in the atmosphere. When the jet stream above provided strong outflow, the low-pressure system could maintain itself. When that outflow weakened or shifted, the low-pressure centre began to lose its structure. The high-pressure systems around Fern were also in motion, even if that motion was slow. As they drifted or weakened, the shape of the pressure gradient changed. The tug-of-war shifted, the balance of forces adjusted. From a forecasting perspective, tracking these pressure systems is one of the main ways meteorologists anticipate changes in weather. Pressure maps show where the highs and lows are, how strong they are, and how they are likely to move. The spacing between the lines of equal pressure, called isobars, gives an indication of how strong the winds might be. Closely spaced lines suggest a steep gradient and stronger winds. Widely spaced lines suggest a gentler flow. During Fern's passage, the isobars in certain regions were packed tightly together, reflecting the strong gradient between the high and low pressure areas. This visual cue matched what people felt on the ground, with brisk winds and a sense of the air being in motion even when precipitation was light. There's also an interesting interplay between pressure and temperature that adds another layer to this story. Cold air tends to be associated with higher pressure and warm air with lower pressure, but this isn't a strict rule. The vertical structure of the atmosphere matters. A region can have low pressure at the surface and high pressure aloft, or vice versa, depending on how air is moving in different layers. This layered structure can create situations where surface conditions and upper-level patterns seem out of sync. A storm might appear to weaken at the surface while still being supported by strong winds aloft, or a high-pressure system at the surface might be undercut by a developing low-pressure area above. In Fern's case, the alignment between surface pressure systems and upper-level support was one of the reasons the storm was able to sustain itself for as long as it did. The tug-of-war wasn't just happening at ground level, it was happening through a deep column of the atmosphere. It's also worth considering how these pressure systems fit into the larger circulation of the planet. High and low pressure are not random features. They are part of a global pattern driven by the uneven heating of the Earth. Warm air rises near the equator, creating a belt of low pressure. It flows poleward aloft, cools, and sinks in the subtropics, creating belts of high pressure. From there, it flows back toward the equator and toward the poles at the surface, setting up the major wind patterns of the world. Within this broad framework, smaller scale highs and lows form and move, interacting with each other and with the larger pattern. Fern's tug-of-war was a local expression of this global circulation, a small drama playing out within a much bigger system. For people experiencing the storm, this global context is mostly invisible. What's felt is the local outcome, the wind pushing against a door, the snow drifting across a road, the way the air feels heavier or lighter, calmer or more restless. But behind those sensations is this constant push and pull, this balancing act that never really stops. Even on the calmest day, pressure systems are shifting somewhere, setting the stage for future changes. One of the quiet consequences of this tug-of-war is how it shapes the boundaries of weather systems. The line between a high-pressure dominated region and a low-pressure dominated region is often where fronts form. These fronts are the dividing lines between different air masses, and they are where much of the visible weather occurs. As Fern moved, its associated fronts marked the edges of the tug-of-war. On one side, the air was colder, drier, and often clearer. On the other, it was warmer, moister, and more cloud-filled. The front itself was a zone of lifting and mixing, a place where the contest between sinking and rising air played out in a narrow band. These boundaries can be sharp or gradual, depending on how strong the contrast is and how the winds are aligned. In some places, Fern's fronts passed with a noticeable shift in wind and temperature. In others, the change was more subtle, spread out over hours. This variability is another reminder that the atmosphere doesn't operate in neat uniform patterns. Even within a single storm, the tug-of-war can feel different from place to place, depending on local geography, timing, and the precise arrangement of the larger scale systems. As Fern's low-pressure centre eventually moved into an environment where the surrounding high-pressure systems were weaker or positioned differently, the balance began to change, the gradient lessened, the winds eased, the inflow of air slowed. Without the same level of support, the storm began to lose its organisation. This is how most storms end, not with a dramatic moment, but with a gradual shift in the forces that sustain them. The rope in the tug-of-war goes slack. The pull on both ends diminishes. The system relaxes back toward a more neutral state. Even then, the pressure systems don't disappear. They simply transform, merge, or drift into new positions, ready to play their roles in whatever comes next. There's something quietly reassuring in this. The atmosphere is always working toward balance, even if the path it takes involves moments of intensity and disruption. The tug-of-war is not a battle with a winner and a loser. It's a process of adjustment, of constant negotiation between different parts of the system. Fern was one round in that ongoing negotiation. High pressure pushed, low pressure pulled, air flowed, clouds formed, snow fell, winds blew, and then, as the balance shifted, the system moved on. You might imagine the atmosphere as a vast field of invisible hills and valleys made of pressure instead of land. Air rolls down from the hills into the valleys, rises, and then spreads out again, reshaping the landscape as it goes. Storms like Fern are the visible expressions of that rolling motion, the moments when the slopes are steep and the movement is fast. Speed is one of the things that often catches people off guard when a storm begins to grow. One day, it looks like a modest system, a patch of unsettled weather that might bring some wind or snow. The next, it's dominating forecasts, drawing attention and reshaping plans. Fern followed that pattern, not because it broke the rules of the atmosphere, but because several of those rules happened to line up in a way that allowed the storm to gather strength faster than usual. To understand how a storm can intensify quickly, it helps to think about what intensify really means in this context. For a mid-latitude winter storm, intensification usually refers to a drop in surface pressure at the storm's centre and an increase in the strength of its circulation. Lower pressure draws in air more strongly. Stronger inflow leads to faster winds. Faster winds can lift more air, which can create more clouds and precipitation. It's a chain of cause and effect, with each link reinforcing the next. Fern's rapid development was the result of several of these links tightening at the same time. One of the most important factors was the temperature contrast across the storm. As we've already touched on, storms thrive on differences. The greater the contrast between warm and cold air, the more energy is available for the system to use. In Fern's case, cold air had pushed southward, while relatively warm, moist air remained in place to the south and over nearby water. This created a sharp boundary, a zone where the atmosphere was primed for strong upward motion. When warm air is forced to rise over cold air, it doesn't just drift upward gently. If the contrast is strong enough, the lifting can be vigorous. As the air rises, it expands and cools, and the moisture within it condenses into clouds and precipitation. That condensation releases latent heat, warming the surrounding air and making it more buoyant. More buoyant air rises more readily, which can further lower the pressure at the surface below. This is one of the key feedback loops in storm intensification. Rising air lowers surface pressure. Lower pressure draws in more air. Some of that incoming air is warm and moist, which rises and releases more heat. The cycle continues. For Fern, this loop was particularly effective because the environment around the storm supported it from multiple angles. The surface conditions provided contrast and moisture. The upper atmosphere provided a pathway for rising air to escape. That upper level support is crucial. If air rises at the surface but has nowhere to go aloft, it can pile up, increasing pressure and choking off the storm's growth. In Fern's case, the jet stream was positioned in a way that encouraged air to spread out at higher altitudes. This outflow acted like a vent, allowing the storm to breathe. The alignment between surface and upper level features is sometimes referred to as a stacked or phased system. It means that the low pressure area at the surface and the supportive winds aloft are working together rather than at cross purposes. When this happens, storms often have an easier time intensifying. Another factor in Fern's rapid growth was the availability of moisture. Dry air can limit a storm's ability to build clouds and precipitation, even if other conditions are favourable. Moist air, on the other hand, provides both the raw material for clouds and the latent heat that fuels rising motion. As Fern developed, it had access to a steady supply of moisture, drawn in from lower latitudes and over open water. This moist air was funneled into the storm's circulation, lifted, cooled, and condensed. Each round of condensation released energy back into the system, helping maintain the upward motion and the low pressure at the core. This process doesn't always happen evenly. Often, storms develop areas of particularly strong rising motion, known as bands or sectors, where clouds and precipitation are more intense. These areas can act like engines within the larger system, driving further intensification. In Fern's case, such bands formed along the boundary between warm and cold air. As these zones of rising motion became more organised, they helped focus the storm's energy, making its circulation more efficient. The shape and movement of the storm also played a role. As Fern's circulation tightened, the winds around its centre began to wrap more closely around the low-pressure core. This can help concentrate the pressure drop, much like tightening a spiral can bring its centre into sharper focus. This tightening can be influenced by what's happening above the storm. When the winds aloft are arranged in a way that encourages divergence, meaning air spreading outward, it can help pull the surface circulation upward and inward, sharpening the storm's structure. Timing was another critical element. Fern didn't develop in isolation. It emerged in a window where the broader atmospheric pattern was particularly supportive. The jet stream's detour, the position of nearby high-pressure systems, and the availability of cold and warm air masses all aligned within a relatively short period. If any one of these elements had arrived earlier or later, the outcome might have been different. The storm might have struggled to organise, or it might have intensified more slowly. Instead, the pieces came together in a way that allowed the system to take advantage of the available energy before the pattern shifted. This sensitivity to timing is one of the reasons why storms can sometimes surprise even experienced forecasters. The atmosphere is a complex system with many moving parts. Models can simulate how those parts might interact, but small differences in initial conditions can lead to noticeable differences in outcomes, especially when the system is near a threshold between growth and decay. Another layer to Fern's intensification involved the vertical structure of the atmosphere. It's not just the temperature at the surface that matters. The way temperature changes with height can determine how easily air can rise. If the air aloft is relatively cold compared to the air near the surface, the atmosphere is said to be unstable. In an unstable atmosphere, rising air tends to keep rising because it remains warmer and lighter than its surroundings. This can enhance cloud formation and precipitation. In Fern's case, the presence of colder air aloft, associated with the jet stream trough, helped create a more unstable environment. This made it easier for the warm, moist air near the surface to rise, supporting the storm's development. At the same time, the cold air near the surface on the storm's northern and western sides helped maintain the temperature contrast that fueled the system. This combination of cold above and cold below, with warm air in between in certain sectors, created a layered structure that was particularly favourable for strong upward motion in specific regions of the storm. The land and sea beneath the storm also influenced how quickly it could intensify. As Fern moved over areas with relatively warm water or over land that retained some heat, the surface could continue to supply energy to the lower atmosphere. This helped keep the boundary between warm and cold air sharp. In contrast, if a storm moves over very cold land or ice-covered water, the surface may not be able to provide as much energy, which can slow or halt intensification. Fern's path allowed it to maintain contact with regions that could still contribute heat and moisture, at least during its most active phase. There's also a geometric aspect to how storms grow. The size and shape of the circulation can influence how efficiently air is drawn in and lifted. A compact, well-organised system can sometimes intensify more quickly than a sprawling, diffuse one, simply because the flows are more focused. As Fern's circulation became better defined, its core pressure dropped more rapidly. This drop increased the pressure gradient around the storm, which in turn strengthened the winds. Stronger winds helped draw in more air and moisture, reinforcing the storm's structure. This kind of positive feedback can lead to what meteorologists sometimes call rapid intensification, though the term is more commonly associated with tropical systems. In mid-latitude storms, the same basic idea applies. When the environment supports multiple reinforcing processes at once, the system can strengthen at a pace that feels sudden. For people on the ground, this rapid growth can translate into forecasts that change quickly. A system that was expected to bring light snow might suddenly be projected to deliver heavier amounts. Wind advisories might be upgraded. Travel plans might need to be reconsidered. This can feel unsettling, but it's a reflection of how dynamic the atmosphere is. The storm isn't deciding to intensify. It's responding to the conditions around it, conditions that are themselves evolving. Another subtle contributor to Fern's growth was the way it interacted with other smaller disturbances in the atmosphere. The atmosphere is rarely smooth. It's full of ripples, short waves, and localized features that can merge with or enhance larger systems. As Fern developed, it absorbed or interacted with some of these smaller scale features. Each interaction added a bit more energy or organization to the storm, helping it consolidate its structure. This merging process is another example of how storms are not isolated objects, but parts of a larger flow. They can grow by drawing in not just air and moisture, but also momentum and structure from their surroundings. From a broader perspective, Fern's quick intensification was a reminder of how interconnected the system is. Surface conditions, upper-level winds, moisture sources, temperature gradients, and even the shape of the land all played roles. None of these factors alone would have guaranteed rapid growth. Together they created a window of opportunity that the storm moved through. As that window began to close, the pace of change slowed. The jet stream shifted. The temperature contrast softened. The moisture supply became less direct. The feedback loops that had been so efficient at strengthening the storm began to weaken. This transition is often just as gradual as the intensification itself can be sudden. The storm doesn't simply stop. It evolves, losing some features, gaining others, and eventually blending back into the broader flow of the atmosphere. Looking back at Fern's rapid growth, it's tempting to label it as unusual or extreme. In some respects it may have been, but in another sense it was a textbook example of what can happen when the atmosphere's ingredients are well matched and well timed. The lesson here is not that storms are unpredictable, but that they are sensitive to small shifts in large patterns, sensitive to the timing of air mass movements, sensitive to the alignment of features across different layers of the sky. This sensitivity is part of what makes studying weather both challenging and rewarding. It's a field where patterns and principles provide guidance, but details matter, and the details are always changing. Fern's quick rise was not the result of a single dramatic cause, but of a convergence, a meeting of contrasts, flows, and supports that for a time allowed the storm to draw deeply from the atmosphere's stored energy. The storm took what the system offered and shaped it into motion and weather, and as those offerings changed, so did the storm itself. What people remember most about a storm is rarely the pressure charts or the satellite images. It's the way the world felt while it was happening, the sound of wind in the trees, the scrape of ice under boots, the way snow changed familiar streets into something quieter and stranger. For Fern, these surface details were where all the invisible processes we've been following finally showed themselves, turning shifts in air and energy into experiences that pressed against windows, roads, and daily routines. Snow, ice, and wind are not separate characters in a storm story. They are different expressions of the same underlying system, shaped by how temperature, moisture, and motion line up at just the right, or wrong, moments. The foundation of everything that fell from the sky during Fern's passage was moisture. Water vapour lifted from oceans, lakes, and even damp ground travelled with the moving air into the storm's circulation. As that air rose, it cooled, and the vapour began to change form. But what it changed into depended on the temperature of the layers it passed through on the way down. In the coldest parts of the storm, the air was below, freezing from cloud level all the way to the ground. Here, the moisture condensed directly into ice crystals. These crystals grew, branched, and collided with one another, forming the delicate structures we recognise as snowflakes. By the time they reached the surface, they had often clustered together into soft, drifting flakes that settled quietly on whatever they touched. In other regions, the story was more complicated. The air near the surface might have been cold enough to freeze, while a layer of warmer air sat above it. In this case, snowflakes formed in the clouds, then melted into raindrops as they passed through the warm layer. When those drops fell back into the cold air near the ground, they became supercooled, liquid water at temperature below freezing. When they touched a surface, they froze instantly, forming a thin, clear layer of ice. This kind of precipitation, often called freezing rain, can be one of the most disruptive forms of winter weather. It doesn't pile up softly like snow. It coats everything it touches: roads, sidewalks, power lines, tree branches, even the fine twigs at the ends of limbs. The result is a landscape that looks polished and glassy, but feels brittle and dangerous. Sleet, another form that appeared in some areas during Fern's passage, sits between these two. It forms when snowflakes melt into raindrops in a warm layer, then refreeze into small ice pellets before reaching the ground. These pellets bounce when they land, creating a sound that's somewhere between rain and hail, and they can accumulate into a crunchy, slippery layer that's harder to clear than snow. The specific mix of snow, ice, and sleet that people experienced depended on the exact temperature profile of the atmosphere above them at a given moment. And that profile could change over the course of hours or even minutes as the storm moved and evolved. What made Fern's impacts feel particularly strong in many places was the way these forms of precipitation combined with wind. Wind is the atmosphere's way of redistributing pressure differences, and in a strong storm those differences can be pronounced. The tighter the pressure gradient around the low pressure centre, the faster the air moves. As Fern intensified, the pressure at its core dropped, and the surrounding high-pressure areas maintained their strength. This created a steep gradient which translated into brisk, sometimes powerful winds at the surface. Wind changes how snow behaves. In calm conditions, snow falls more or less straight down, accumulating where it lands. In windy conditions, it becomes a moving thing. Flakes are carried sideways, swirled into drifts and piled up against buildings, fences and natural obstacles. Some areas end up with deep banks while others are scoured nearly bare. This unevenness can make a storm feel harsher than the snowfall totals alone might suggest. A road might be technically ploughed, but drifting snow can quickly refill it. A sidewalk might look clear, but wind-blown snow can cover it again in minutes. Wind also changes how cold feels. Moving air pulls heat away from the body more quickly than still air, creating what's known as wind chill. Even if the thermometer shows a certain temperature, the combination of cold and wind can make it feel significantly colder on exposed skin. During Fern, this added to the sense of intensity, especially in open areas where the wind had little to slow it down. Ice and wind together can be an especially heavy combination. When freezing rain coats tree branches and power lines, it adds weight. That weight can bend branches, snap them, or pull lines down. If the wind then pushes against those already strained structures, the stress increases. This is often when outages and damage occur, not just because of the ice or the wind alone, but because of how they work together. In regions affected by this combination during Fern, the storm left behind more than just a changed landscape. It created moments of stillness where lights went out and the usual hum of electronics and appliances faded. In those moments, the sound of the wind and the occasional crack of ice-shifting branches became more noticeable, a reminder of how present the atmosphere can feel when its effects reach into everyday systems. Another factor that made Fern hit hard was its reach. The storm wasn't a narrow band that affected only a small area. It covered a broad region, bringing different forms of winter weather to different places. This meant that its overall impact was spread across many communities at once, stretching resources and making coordination more challenging. When a storm is widespread, there's less opportunity for unaffected areas nearby to provide immediate support. Road crews, utility workers, and emergency surveyors are often dealing with conditions across large distances, rather than being able to focus on a single, concentrated zone. The timing of the storm also played a role in how it was felt. If heavy snow or ice arrives overnight, people wake up to a changed world, and the disruption is immediate. If it arrives during a busy part of the day, it can intersect directly with travel, work and school schedules, amplifying the sense of impact. Fern's most active periods aligned in some places with times when people were on the move. This turned what might have been a manageable accumulation into a more complicated situation, with traffic slowing, public transportation delayed, and daily routines interrupted. From a meteorological perspective, one of the reasons Fern was able to produce such a variety of impacts was the structure of its circulation. The storm had well-defined sectors, each with its own characteristics. On the colder side, snow dominated. On the warmer side, rain or mixed precipitation was more likely. Near the boundary between these sectors, conditions could shift back and forth, leading to periods of snow changing to ice and back again. These transition zones are often where the most challenging conditions occur. Roads can go from wet to icy in a short span of time. Surfaces that were previously cleared can become slick again. The uncertainty itself becomes part of the experience as people try to anticipate what will happen next. The wind patterns within the storm also created areas of convergence and divergence, where air flowed together or spread apart. In convergent zones, air was forced upward more strongly, leading to heavier precipitation. In divergent zones, the precipitation was lighter or more intermittent. This led to bands of more intense snow or ice, sometimes just a few miles wide, embedded within the larger storm. For those under one of these bands, Fern felt particularly relentless. For those just outside, it might have seemed milder by comparison. This kind of banding is a reflection of how organized the storm's circulation had become. It's a sign that the system is efficiently channeling energy and moisture into specific pathways, rather than spreading them evenly across its entire area. Another element that contributed to Fern's impact was the duration of certain conditions. As we've seen, the jet stream's shape and the surrounding pressure systems allowed the storm to move more slowly than it might have otherwise. This meant that snow, ice and wind persisted for longer periods in some regions. A few hours of moderate snow can be manageable. A full day or more can lead to significant accumulation. Similarly, a brief period of freezing rain might glaze surfaces lightly, while an extended period can build up layers of ice that become structurally significant. This lingering effect turned Fern from a passing event into something that felt more like a phase of the season, a stretch of time where the weather held on and asked people to adjust rather than simply wait it out. The way the storm interacted with local geography added another layer. In open, flat areas, the wind had room to build speed, pushing snow into long, low drifts that stretched across fields and roads. In wooded or urban areas, buildings and trees created turbulence, leading to swirling gusts and uneven accumulation. Hills and ridges altered the flow of air, sometimes enhancing snowfall on their windward sides, and creating calmer, drier zones on the leeward sides. These small-scale variations meant that even within a single town, the experience of Fern could differ from one neighbourhood to the next. Temperature differences within the storm also influenced how people experienced it over time. In some places, conditions hovered just below freezing for hours. This meant that snow fell, melted slightly on contact with warmer surfaces, and then refroze as temperatures dipped again. The result was a layered surface, part snow, part ice, that was difficult to clear and even harder to walk or drive on safely. This kind of cycling can make a storm feel more punishing, not because it's producing record-breaking amounts of precipitation, but because it's creating surfaces that are persistently slippery and unpredictable. The soundscape of the storm was another part of its presence. Snow falling in still air is often nearly silent, muffling the world and creating a sense of quiet. Wind changes that. It adds a constant rush or howl, punctuated by the rattle of loose objects and the creak of trees. Ice adds its own subtle noises, the faint crackle as branches shift under new weight, the sharp tap of sleet against windows. These sounds become part of how a storm is remembered, especially during the moments when people pause and listen, perhaps late at night or early in the morning when everything else is still. There's also a visual aspect that can make a storm feel more intense. Snow reflects light, brightening the night and softening the edges of everything it covers. Ice reflects light differently, creating sparkles and glints that can make the world look almost unreal. Wind reshapes these surfaces constantly, so the scene outside a window can change from hour to hour. For Fern, these shifting visuals were a sign of the storm's ongoing activity. Even when the heaviest precipitation eased, the wind could keep the landscape in motion, blowing loose snow into the air and reminding everyone that the system was still present. From a broader perspective, Fern's hard-hitting nature was a reflection of how well its internal processes were aligned. The storm had a strong temperature contrast to work with. It had access to moisture. It had upper-level support from the jet stream. It had a persistent pressure gradient to drive winds. These factors combined to produce a system that was efficient at turning atmospheric energy into tangible effects on the ground. The snow, ice, and wind were not random. They were the natural outcomes of that efficiency. It's also worth noting how human systems intersected with these natural ones. Roads, power grids, communication networks, and buildings are all designed with certain weather conditions in mind. When a storm like Fern pushes those conditions toward the edge of what's expected or comfortable, the interaction becomes more noticeable. A few inches of snow might be routine in one place, and a major disruption in another. A thin layer of ice might be manageable on a quiet rural road, and a serious hazard on a busy highway. The same storm can feel very different depending on where and how it intersects with the built environment. This interaction can amplify the sense that a storm hit hard, even if its meteorological characteristics are not unprecedented. Impact is a combination of physical conditions and human context. As Fern moved on and conditions began to ease, what remained was often a landscape marked by these interactions. Piles of ploughed snow along roads, branches bent or broken by ice, clear patches where wind had scoured surfaces bare. These traces are the visible signatures of the storm's passage, the record of how air, water and temperature combined for a time to reshape the surface of the world. Looking back, it becomes clear that Fern's strength was not a single, simple thing. It was a combination of form, motion and duration. Snow that fell steadily, ice that coated and lingered, wind that pushed and reshaped. Each of these elements has its own story, its own set of conditions that allow it to form. Fern brought them together in a way that made the storm feel comprehensive, touching many aspects of daily life at once. Looking back after a storm has passed, it's almost impossible not to ask the question, could we have seen this coming sooner? Was there a moment, days or even weeks earlier, when Fern was already written into the atmosphere, waiting for someone to notice? The idea of prediction carries a certain comfort. It suggests that the world, even in its most restless moments, follows patterns that can be read, understood, and maybe even anticipated. The truth sits somewhere between certainty and mystery. Weather forecasting is not about knowing exactly what will happen. It's about narrowing down what is likely to happen, using the best tools available to peer into a system that is always in motion. At the heart of modern prediction are numerical weather models. These are vast mathematical representations of the atmosphere, run on powerful computers that divide the sky, the land and the oceans into millions of small grid points. At each of these points, the model keeps track of variables like temperature, pressure, wind speed, humidity, and more. It then uses the laws of physics to calculate how those variables should change over time. In theory, if you knew the exact state of the atmosphere everywhere, down to the smallest detail, you could predict how it would evolve far into the future. In practice, that level of precision is impossible. The atmosphere is too large, too complex, and too sensitive to tiny changes. Even the most advanced observing networks can only sample a fraction of what's happening at any given moment. This sensitivity to small differences is one of the defining features of weather systems. A slight change in temperature here, a subtle shift in wind there, can grow over time into a noticeable difference in how a storm develops. This idea is often captured in the phrase, the butterfly effect, which suggests that small influences can have large consequences in complex systems. For Fern, this meant that while the broad pattern that supported a winter storm could be identified several days in advance, the exact details of its path, strength, and impacts took longer to come into focus. Forecasts usually begin with a wide lens. Several days out, meteorologists look at the large-scale patterns. Where is the jet stream likely to be? Are there signs of strong temperature contrast developing? Are pressure systems lining up in a way that favours storm formation? These questions can often be answered with a fair degree of confidence, even when the details remain fuzzy. In Fern's case, the larger pattern was visible ahead of time. Models showed a dip in the jet stream, a push of cold air, and a developing low-pressure system along the boundary between warm and cold air. These are classic ingredients for a winter storm. So, at a broad level, the potential was there. What was harder to pin down was how efficiently those ingredients would come together. Would the low-pressure system deepen quickly or slowly? Would the jet stream provide strong upper-level support or shift away? Would the cold air arrive early enough to turn rain into snow, or would temperatures hover near the freezing point? These are the kinds of details that often remain uncertain until closer to the event. They depend on interactions between different layers of the atmosphere, and those interactions can be influenced by small-scale features that models struggle to represent perfectly. One of the ways meteorologists deal with this uncertainty is by using what's called ensemble forecasting. Instead of running a single model simulation, they run many. Each simulation starts with slightly different initial conditions, reflecting the uncertainty in the observations of the current atmosphere. The collection of these runs produces a range of possible outcomes. If most of the simulations show a similar result, confidence in that outcome increases. If the simulations diverge widely, it's a sign that the atmosphere is in a sensitive state, where small differences could lead to very different scenarios. In the days leading up to Fern, ensemble forecasts showed a range of possibilities. Some runs indicated a strong, slow-moving storm with widespread snow and wind. Others suggested a weaker system that would pass through more quickly, with mixed precipitation and less impact. As time went on and more observations were fed into the models, the range began to narrow. The atmosphere itself was revealing more of its intentions, and the simulation started to agree on a more intense outcome. This process is a bit like focusing a lens. At first, the image is blurry. You can see the general shape, but not the fine details. As you adjust, the picture becomes clearer. Forecasts work in a similar way, becoming more precise as the event draws closer and more data becomes available. One of the key sources of that data is the global network of weather observations. Satellites scan the Earth from orbit, measuring cloud cover, temperature and moisture. Weather balloons are launched twice a day from hundreds of locations, carrying instruments high into the atmosphere to record temperature, pressure and wind. Ships, aircraft and surface stations add their own measurements. All of this information is fed into the models to create a snapshot of the current state of the atmosphere. The better that snapshot, the better the starting point for the forecast. Even with this extensive network, there are gaps. Some regions, especially over the open ocean or in remote areas, have fewer direct observations. Satellites help fill in many of these gaps, but they don't measure everything directly. They infer conditions based on the radiation coming from the Earth and the atmosphere. For a storm like Fern, which drew moisture and energy from over water, the quality of observations in those source regions can influence how well models represent the storm's potential. If the model underestimates the amount of moisture or heat available, it might predict a weaker system than what actually develops. Another challenge in early prediction is the representation of small-scale features. Models are built on grids, and even the highest resolution global models can't capture every hill, valley or narrow band of clouds. These smaller features can influence where and how strongly precipitation falls, especially in complex terrain. As Fern approached, local forecasting centres often used higher resolution regional models to refine their predictions. These models focus on a smaller area and use finer grids, allowing them to represent local geography and small-scale atmospheric features more accurately. This combination of global and regional modelling is part of how forecasts evolve from broad outlooks to more detailed, location-specific predictions. There's also a human element to forecasting that's easy to overlook. Meteorologists don't just read model output, they interpret it. They look for patterns, compare different models, and use their experience to judge which scenarios are more plausible given the current setup. For example, if one model run shows a particularly extreme outcome but most others do not, a forecaster might treat that result with caution. On the other hand, if multiple models and ensemble members converge on a similar intense scenario, that can prompt an increase in alerts and advisories. In Fern's case, this interpretive process played out over several days. Early on, the possibility of a notable winter storm was flagged. As the models began to align on a stronger, slower-moving system, the messaging shifted to emphasize potential impacts. This gradual escalation is part of how forecasting communicates uncertainty. Instead of presenting a single, definitive outcome far in advance, forecasts often start with a range of possibilities and then narrow that range as confidence grows. From the perspective of someone waiting for the storm, this can feel like the forecast is changing or being updated frequently. In reality, it's the reflection of a dynamic system becoming clearer as it unfolds. It's also worth noting that prediction is not just about the storm itself. It's about the impacts. Snowfall amounts, ice accumulation, and wind speeds can vary significantly over short distances. Forecasting where the heaviest band of snow will set up, or where temperatures will hover right at the freezing point, is often one of the hardest parts of winter weather prediction. For Fern, these impact-focused questions were particularly important. A small shift in the storm's track could mean the difference between heavy snow in one region and freezing rain in another. That difference has major implications for travel, infrastructure, and safety. Meteorologists often communicate this by highlighting zones of greatest uncertainty, areas where the forecast is especially sensitive to small changes. These zones can move as the storm evolves, and they are often the focus of close monitoring in the final hours before and during the event. Looking further back in time, beyond the immediate days leading up to Fern, there's also the realm of longer-range forecasting. Seasonal outlooks and climate patterns can indicate whether a winter is likely to be colder, warmer, wetter, or drier than average. These outlooks are based on large-scale features like ocean temperature patterns and long-term atmospheric trends. Such forecasts can't predict individual storms, but they can suggest whether the overall environment is more or less favourable for systems like Fern to develop. In the season when Fern occurred, some of these broader indicators pointed toward a pattern that could support active winter weather in certain regions. This kind of background information can help set expectations. It doesn't tell you when a storm will arrive, but it can hint at whether the season might be more likely to produce them. There's also an important distinction between predicting the atmosphere and predicting how people will experience it. Even if a storm is well forecast, its impact can still vary depending on timing, preparedness, and local conditions. A storm that arrives when roads are clear and temperatures are cold enough for salt to work might be easier to manage than one that arrives during rush hour, or when temperatures hover near freezing. Forecasts can anticipate the weather, but the intersection with human systems adds another layer of complexity. This is why communication is such a big part of modern forecasting. It's not just about stating what the atmosphere is likely to do, it's about conveying what that might mean for people. Will travel be difficult? Is there a risk of power outages? Should schools consider closures? For Fern, these questions became part of the public conversation as confidence in the forecast grew. Advisories and warnings were issued, updated and refined, reflecting both the evolving understanding of the storm and the desire to give people enough time to prepare. In hindsight, it can be tempting to look for a single moment when Fern could have been seen clearly. The reality is more gradual. The storm's potential emerged in stages, becoming clearer as the atmosphere itself organised. There were signs early on that a winter storm was possible. There were fewer signs that it would intensify as quickly or impact as broadly as it eventually did. Those details came into focus only as the system moved closer and the models had more concrete information to work with. This layered approach to prediction is a reflection of how the atmosphere operates. Large-scale patterns set the stage. Medium-scale features shape the plot. Small-scale interactions determine the fine details. Forecasting follows the same structure. It starts with the broad strokes and works its way toward the specifics. It's also a reminder that prediction is not about control. Even with all the technology and knowledge available, the atmosphere remains a system with its own internal dynamics. We can observe it, model it, and anticipate its behaviour, but we can't make it follow a script. In that sense, Fern was both predictable and surprising. Predictable in that the ingredients for a winter storm were visible ahead of time. Surprising in how efficiently those ingredients came together, and how strongly the system expressed itself in certain places. As forecasting tools continue to improve, the window of confident prediction will likely continue to expand. Models will become more detailed, observations will become more comprehensive, communication will become more refined, but there will probably always be an element of uncertainty, especially in the fine details that matter most to people on the ground. The atmosphere's sensitivity to small changes is not something that can be completely eliminated. As you reflect on Fern and the question of whether it could have been predicted earlier, it can be helpful to think of forecasting as a conversation rather than a proclamation. The atmosphere offers hints. Models interpret those hints. Forecasters translate them into guidance. The picture becomes clearer over time, but it rarely snaps into perfect focus all at once. Long before a single cloud thickened or a forecast hinted at winter weather, the atmosphere was already operating within a much larger set of rhythms. These rhythms don't announce themselves with sudden changes or dramatic moments. They unfold slowly, over months, years, and even decades, shaping the background conditions that make certain kinds of storms more or less likely to appear. Fern did not emerge in isolation. It stepped onto a stage that had been quietly prepared by broader climate patterns that influence how air and water move around the planet long before they ever meet in a single storm system. Climate patterns are not the same as daily weather. Weather is what you feel when you step outside: the temperature, the wind, the cloud cover, the precipitation. Climate patterns are the tendencies, the long-term behaviours of the system. They describe how the atmosphere and oceans usually arrange themselves over time, how energy is typically distributed, and how certain regions tend to experience particular types of conditions more often than others. One of the most important players in this larger picture is the ocean. The surface of the ocean is not uniformly warm or cold. Different regions heat up and cool down at different rates, influenced by sunlight, currents, and the movement of water between the surface and the depths. These differences in temperature can persist for months or years, creating patterns that ripple outward into the atmosphere above. When a region of the ocean is warmer than average, it tends to warm the air above it. Warm air rises more easily, lowering surface pressure and encouraging the formation of clouds and storms. When a region is cooler than average, the air above it is often more stable, with higher pressure and fewer storms. In this way, patches of warm and cool water can act like subtle signals to the atmosphere, nudging winds and pressure systems into certain arrangements. One of the most well-known examples of this kind of ocean-atmosphere interaction is the cycle often referred to as El Niño and La Niña. These are phases of a broader pattern involving the tropical Pacific Ocean. During an El Niño phase, the surface waters in parts of the Pacific become warmer than usual. During a La Niña phase, they become cooler. These changes may seem far removed from a winter storm like Fern, but they can have wide-reaching effects. By altering where heat is released into the atmosphere, they can shift the position of major wind patterns, including the jet stream. A change in the jet stream's typical path can influence which regions tend to receive more storms, which tend to be colder or warmer, and how often certain weather patterns repeat. In the season when Fern developed, the broader oceanic pattern helped shape the background flow of the atmosphere. It didn't dictate the exact path of the storm or the precise timing of its intensification, but it influenced the general layout of pressure systems and wind patterns that made the environment more or less supportive of an active winter system. Another large-scale pattern that often plays a role in winter weather is the arrangement of pressure systems in the higher latitudes. There are regions near the poles where low-pressure systems tend to dominate, creating a kind of atmospheric whirlpool of cold air. This is sometimes referred to as the polar vortex, not as a single storm, but as a broad circulation pattern that helps keep cold air contained in higher latitudes. When this circulation is strong and well organised, the cold air tends to stay farther north. When it becomes weaker or more distorted, lobes of cold air can slip southward into regions that usually experience milder conditions. These southward excursions can set the stage for sharp temperature contrasts and, in turn, for strong winter storms. In the period leading up to Fern, the broader pattern of high latitude pressure and winds allowed cold air to move more freely into lower latitudes. This didn't guarantee a storm, but it increased the likelihood that when a low-pressure system did form, it would have access to the kind of cold air that can turn moisture into snow and ice rather than rain. The Atlantic and Pacific Oceans also play their own roles through patterns of temperature variation that can persist over long periods. These patterns can influence where storms tend to track, how much moisture they carry, and how strong they become. For example, warmer than average waters along a storm's typical path can increase the amount of moisture available to be drawn into the system. More moisture means more potential for precipitation, and more latent heat release within the storm, which can support stronger circulation. In Fern's case, parts of the ocean along its moisture pathways were in a state that favoured active exchange between water and air. This didn't create the storm by itself, but it meant that when the storm began to draw in air from those regions, it found a ready supply of energy. There are also patterns in the atmosphere itself that operate on timescales longer than a single storm. One of these is the North Atlantic Oscillation, often described in terms of the pressure difference between regions of the Atlantic. When this difference is strong, it tends to promote faster-moving, more zonal wind patterns. When it is weaker, the flow can become more meandering, allowing cold air to dip farther south and storms to linger longer. Shifts in this kind of pattern can make an entire season feel different. One winter might be marked by frequent, fast-moving storms and mild temperatures. Another might feature fewer storms, but more prolonged cold spells and heavier snowfall. Fern's development took place during a period when the broader atmospheric pattern favoured a more wavy jet stream. This made it easier for cold air to move southward, and for storms to slow down and deepen rather than racing quickly across the map. It's important to emphasise that these climate patterns don't act like switches that turn storms on or off. They are more like the background music in a room. They set a mood, but they don't determine exactly what will be said or done. The specific details of a storm, its track, its strength, its timing, are shaped by more immediate short-term interactions. Still, the mood matters. A season with a background pattern that favours strong temperature contrasts and slow-moving systems is more likely to produce storms like Fern than a season where the atmosphere is more uniform and fast-flowing. Another layer to this stage setting comes from the long-term changes in the climate system itself. Over decades, the average temperature of the planet has been rising. This doesn't mean that cold weather disappears. It means that the baseline from which weather events occur is shifting. Warmer air can hold more moisture. For every degree of warming, the atmosphere's capacity to carry water vapour increases. This means that when storms do form, they have the potential to produce heavier precipitation, whether that precipitation falls as rain or snow, depending on the temperature. In winter, this can lead to an interesting and sometimes counterintuitive effect. In regions where temperatures remain cold enough for snow, a warmer, moister atmosphere can actually lead to heavier snowfall, because there is more water available to be turned into snowflakes. In regions where temperatures hover near freezing, it can mean a greater risk of freezing rain and ice, as small shifts in temperature determine the form of the precipitation. Fern's mix of snow and ice in different regions reflected this delicate balance. The broader climate context, with its influence on temperature and moisture availability, helped shape the range of conditions that the storm was able to produce. There is also the question of how changing climate patterns might influence the behaviour of the jet stream itself. As we mentioned earlier, some research suggests that rapid warming in the Arctic could reduce the temperature contrast between the poles and the equator. This contrast is one of the main drivers of the jet stream's strength. If that contrast weakens, the jet stream may become slower and more prone to developing large waves. A slower, wavier jet stream can lead to more persistent weather patterns, where conditions stay the same for longer periods of time. This is an area of ongoing study and debate within the scientific community. The atmosphere is influenced by many factors, and teasing out the specific role of long-term warming in changes to jet stream behaviour is complex. Still, the idea that the background flow of the atmosphere might be shifting over time adds another dimension to the story of storms like Fern. It suggests that individual events are part of a larger evolving system, one that is not static but changing in subtle and not so subtle ways. From a human perspective, this can make the experience of weather feel different from one generation to the next. Stories of past winters, of storms that were once considered rare or extreme, may become more or less common as the baseline conditions shift. In Fern's case, the storm occurred within a climate system that is already different from what it was several decades ago. The oceans are warmer, the atmosphere holds more moisture. These changes don't dictate the exact form of any single storm, but they influence the pool of energy and water that storms can draw from. There is also a slower, quieter pattern at work in how land surfaces interact with climate. Snow cover, soil moisture, and vegetation all influence how heat is absorbed and released. A landscape covered in snow reflects more sunlight, keeping the surface cooler. Bare ground absorbs more heat, warming the air above it. These surface conditions can feed back into the atmosphere, reinforcing cold or warm patterns. A snowy region can help maintain cold air, while a snow-free region can moderate it. In the lead up to Fern, the distribution of snow cover and soil moisture in different regions influenced how cold air moved and how readily it could be modified by the surface. This is another example of how the stage for a storm is set by a combination of factors that extend beyond the immediate atmosphere. Climate patterns also shape how people and infrastructure are prepared for storms. Regions that regularly experience heavy snow often have systems in place to deal with it. Regions where winter storms are less common may be more vulnerable when one does occur. This human layer is not part of the climate system itself, but it is part of how storms are experienced. A storm of a certain intensity can feel routine in one place and extraordinary in another, depending on expectations and preparedness. When we talk about the stage being set, we are talking about both the physical environment and the social one. The atmosphere may provide the script, but the impact of the performance is shaped by the audience and the setting. Another important climate pattern that influences winter storms is the distribution of sea ice in the polar regions. Sea ice acts as a barrier between the relatively warm ocean and the cold air above. When ice cover is extensive, it limits the amount of heat and moisture that can be transferred from the ocean to the atmosphere. When ice cover is reduced, more open water is available to release heat and moisture into the air. This can influence the development of pressure systems and the movement of cold air. Changes in sea ice patterns can therefore have ripple effects on weather far from the poles. This is another area where long-term climate changes intersect with the shorter-term dynamics of storms. Fern's story sits within this broader context. The specific details of its formation and path were determined by immediate atmospheric conditions, but the backdrop against which those details played out was shaped by longer-term patterns in ocean temperatures, ice cover, and atmospheric circulation. There is a tendency, when looking at a single storm, to focus on what made it unique. What made it stronger, or slower, or more disruptive than others? That focus is natural, and it's useful for understanding immediate causes and improving forecasts. But there is also value in stepping back and looking at the quieter influences, the patterns that don't make headlines but that shape the probabilities over time. These are the forces that determine whether a season is generally calm or active, mild or harsh. Fern was one event in a long sequence of events, each influenced by the same underlying system. The climate patterns that set the stage for it will continue to influence whatever comes next. As you think about this, it can be helpful to imagine the atmosphere and oceans as parts of a vast, slowly turning machine. Some parts move quickly, like storms and fronts. Others move slowly, like ocean currents and long-term temperature trends. The fast parts are what we notice day to day. The slow parts shape the environment in which those fast parts operate. Neither can be fully understood without the other. A storm like Fern makes more sense when you see it not just as a standalone event, but as a moment in an ongoing flow of energy and patterns that extend far beyond any single winter. From here, the story naturally leads toward a bigger question. If these background patterns are changing, if the stage itself is shifting over time, what might that mean for storms in the future? Will events like Fern become more common, less common, or simply different in character? There is a subtle difference between noticing that a winter feels different and being able to say with confidence that winter itself is changing. One is a personal impression shaped by memory, expectation, and experience. The other is a question that reaches into decades of data, thousands of measurements, and a global effort to understand how a complex system evolves over time. Fern's story naturally leads into this quieter, broader reflection, because a storm doesn't just belong to a single day or even a single season. It belongs to a pattern, and patterns invite comparison. People often remember winters through moments. A year when the snowbanks were taller than cars, a season when the ground barely froze at all, a storm that closed schools for a week, a winter that felt like it never really arrived. These memories form a kind of informal archive, one that lives in conversation and personal history rather than in spreadsheets and graphs. Scientists, on the other hand, look for signals that persist beyond individual memories. They look for trends that show up not just in one place, but across regions and across time. They look for changes that are consistent enough to rise above the natural ups and downs of weather from year to year. One of the clearest trends in the data is that, on average, winters are becoming warmer in many parts of the world. This doesn't mean that cold days or heavy snow have disappeared. It means that when temperatures are averaged over months and years, the baseline is shifting upward. This shift can have different effects depending on where you are. In regions that have traditionally experienced very cold winters, a small increase in average temperature might still leave most days below freezing. In these places, the most noticeable change might be an increase in the amount of moisture the air can hold, leading to heavier snowfall when storms do occur. In regions where winter temperatures often hover near the freezing point, a similar increase can have a very different impact. Here, the line between snow and rain is thin. A slight warming can tip many storms from producing snow to producing rain, or from dry snow to heavy, wet snow or ice. Fern's mix of snow, sleet, and freezing rain in different areas was an example of how sensitive winter weather can be to these small temperature differences. The storm didn't need a dramatic change in climate to produce a wide range of conditions. It just needed the air to sit close to that critical threshold where water changes form. Another trend that has been observed is a change in the timing of winter. In some regions, the first sustained cold and snowfall of the season are arriving later than they used to. In others, spring-like conditions are appearing earlier. This can shorten the period when snow cover is persistent, even if individual storms remain intense. This shift in timing can have ripple effects beyond just how winter feels. Snow cover influences how much sunlight the ground reflects, which in turn affects how quickly the surface warms. It also affects soil moisture, plant growth, and the availability of water in rivers and reservoirs. When snow melts earlier, water can run off more quickly, leading to higher river levels in late winter or early spring, followed by lower levels later in the season. These changes can influence ecosystems, agriculture, and water management in ways that extend far beyond the storm that delivered the snow in the first place. There is also the question of how often certain types of winter weather occur. Some studies suggest that in certain regions, the number of days with snow cover is decreasing, even if the total amount of snow in a season doesn't change as much. This can happen when snow falls in heavier bursts but melts more quickly between storms. This pattern can make winters feel more variable. Instead of a steady, continuous presence of snow, there may be a series of on and off episodes. A storm blankets the ground, a warm spell clears it away, another storm brings it back. For people on the ground, this can feel like winter is less predictable, more changeable. For infrastructure and ecosystems, it can mean more cycles of freezing and thawing, which can be more damaging than consistently cold conditions. Freezing and thawing can weaken roads, stress plants, and affect animals that rely on stable snow cover for insulation or camouflage. These cycles are another area where small changes in average temperature can lead to noticeable differences in daily experience. Another aspect of winter that has drawn attention is the behaviour of the jet stream. As we discussed earlier, the jet stream is driven by the temperature difference between the equator and the poles. Some research suggests that as the Arctic warms faster than lower latitudes, this difference may be decreasing. If that contrast weakens, the jet stream may become slower and more prone to developing large waves. A wavier jet stream can lead to weather patterns that persist for longer periods. Cold air can linger over a region for days or weeks. Warm air can do the same. This kind of persistence can make winter feel more intense in some ways, even as average temperatures rise. A prolonged cold spell can still occur within an overall warmer season. A slow-moving storm can still deliver heavy snow or ice. Fern's slower movement and extended impacts in some areas fit into this idea of persistence. While it's not possible to attribute a single storm to a specific long-term trend, it does provide a tangible example of how a wavy jet stream can shape the experience of winter weather. There is also the role of moisture to consider. A warmer atmosphere can hold more water vapour. This means that when conditions are right for precipitation, there is more potential for heavier amounts. In winter, this can translate into heavier snowfalls in cold regions and more intense rain or ice events in milder ones. The phrase snow drought has even entered some conversations, referring to seasons where total snowfall is low, but when snow does fall, it can come in large, concentrated storms rather than steady, smaller ones. This shift toward more intense events, even as the average changes, is one of the ways climate change is often described. It's not just about gradual warming, it's about changes in variability and extremes. People might experience this as winters that feel less consistent. Fewer days of gentle snow, more days of dramatic swings between cold and mild, more frequent shifts between rain and snow within a single storm. Fern's varied precipitation types and changing conditions over time were a snapshot of this kind of variability. The storm moved through temperature zones that were finely balanced, and small changes in the atmosphere led to different outcomes in different places. There is also a geographical dimension to how winter may be changing. High latitude and high altitude regions tend to experience some of the most pronounced warming. This can affect snowpack in mountain ranges, glaciers, and polar areas. Reduced snow and ice in these regions can influence weather patterns farther away. Snow and ice reflect sunlight, keeping surfaces cooler. When they shrink, more sunlight is absorbed, warming the surface and the air above it. This can feed back into the atmosphere, potentially influencing pressure patterns and wind flows. This kind of feedback is part of what makes the climate system so interconnected. Changes in one region can ripple outward, affecting conditions in another. For winter storms, this means that the environment in which they form and move is not static. The temperature of the ocean, the extent of sea ice, the distribution of snow cover on land, and the structure of the atmosphere are all evolving over time. Another piece of the puzzle is how human activities have altered the landscape itself. Urban areas, with their buildings and paved surfaces, tend to be warmer than surrounding rural areas. This can influence how snow and ice behave locally, sometimes turning what would have been snow into rain, or causing snow to melt more quickly. As cities grow, these local effects can become more pronounced, changing the way winter is experienced in and around urban centres. Fern's impacts likely varied between city cores and outlying areas, not just because of geography, but because of how the built environment interacts with temperature and wind. There's also the matter of observation itself. The way we measure and record winter has changed over time. There are more weather stations now, more satellites, more data. This allows for a more detailed and accurate picture of what's happening, but it also means that comparisons with the distant past need to be made carefully. Despite these complexities, the overall trend of warming winters is well supported by a wide range of observations. The details of how that warming expresses itself, however, can vary greatly from place to place. In some regions, winters may become shorter, but still capable of producing intense storms. In others, the character of winter may shift more noticeably toward rain and milder conditions. In still others, heavy snow may remain a regular feature, but the timing and distribution may change. Fern's story sits within this mosaic of regional differences. It was a winter storm that brought cold, snow and ice to some places, and milder, wetter conditions to others. This diversity of experience is likely to continue, even as the broader trends move in a particular direction. One of the challenges in talking about changing winters is separating what is new from what is part of the natural variability of the system. Winters have always been variable. Some have been harsh, some have been mild. Stormy seasons have followed calm ones and vice versa. What scientists look for is a shift in the baseline, a change in the average and in the frequency of certain types of events over long periods. This requires patience and a large body of data, because the signal of long-term change can be masked by the noise of year-to-year differences. For individuals, this can make the idea of change feel abstract. A single, snowy winter can make it seem like nothing has changed. A string of mild winters can make it feel like winter has disappeared. Both impressions can coexist with a long-term trend that only becomes clear when you step back far enough. Fern, as a single event, doesn't answer the question of whether winter is changing. What it does is provide a point of reference. It becomes part of the growing archive of storms, one more data point in a long record. Over time, patterns emerge from these points. Trends become visible. The background against which future storms unfold becomes clearer. There's also a cultural dimension to this question. Winter is not just a season. It's a part of how people imagine their environment. It's tied to traditions, holidays, sports, and ways of life. Changes in winter weather can affect these aspects of culture in subtle ways. Shorter winters can alter the length of ski seasons. Less reliable snow can change winter festivals. More frequent ice events can influence how communities prepare for storms. These changes can shape how people feel about winter, not just how they experience it physically. Fern, for some, might be remembered as a reminder of what winter used to be like. For others, it might be seen as an example of how winter is still capable of making a strong impression. There is also the perspective of the natural world. Many plants and animals are tuned to the rhythms of winter. They rely on cues like temperature, snow cover, and day length to time their behaviours. Changes in these cues can affect migration, hibernation, and growth cycles. For example, some animals use snow as insulation, burrowing beneath it to stay warm. If snow cover becomes less consistent, those animals may be exposed to colder air. Plants that rely on a period of cold dormancy may respond differently if winters become milder. These ecological responses are part of the broader story of how winter is changing, and they feed back into the system in ways that scientists are still working to understand. In the context of Fern, these larger questions may seem distant. The storm itself was a short-lived event, but it occurred within a living system that is constantly adjusting, and those adjustments can influence what storms look like in the future. As you reflect on this, it can be helpful to hold two ideas at once. One is that winter, as a concept and a season, is still very much present. Cold, snow, and storms have not vanished. The other is that the conditions under which winter unfolds are not fixed. They are influenced by changes in the climate system that operate on timescales much longer than a single storm. Fern was shaped by immediate factors like the jet stream, pressure systems, and moisture supply. But those factors themselves are part of a larger evolving pattern. The question of whether winter is changing the way it behaves doesn't have a single, simple answer. It has many answers, depending on where you are, what you look at, and how far back or forward you consider. What is clear is that winter, like the rest of the climate system, is not static. It is part of a planet that is always in motion, always exchanging energy, always responding to influences from within and beyond. When a storm fades from the forecast and its name slips out of daily conversation, what remains is more than just snowbanks melting or ice cracking away from branches. What remains is a kind of quiet question. What does this moment, this particular arrangement of wind, cold, and moisture suggest about what might come next? Fern, like every storm before it, becomes part of a growing collection of experiences and observations that scientists, planners, and everyday listeners alike use to think about the future. The idea of learning from a storm is not new. Long before satellites and supercomputers, people watched the sky, the wind, and the seasons, noticing patterns and drawing conclusions from what they saw. A harsh winter followed by a mild one, a year with frequent storms followed by a quieter stretch. These observations formed a kind of informal forecasting, grounded in memory and repetition. Today, that process has become more structured and more detailed. Each storm is recorded in layers of data: wind speeds, pressure changes, precipitation amounts, temperature profiles, satellite imagery, radar scans, and model performance are all archived and studied. Fern joined this record, adding its own unique signature to the long history of winter weather. One of the most important things Fern highlights is how sensitive storms are to their environment. The storm did not arise from a single dramatic cause. It emerged because several background conditions aligned. Cold air was available, warm, moist air was nearby. The jet stream took a supportive path. Pressure systems set up a strong gradient. Moisture pathways were open. This alignment is a reminder that future storms will likely continue to be shaped by similar combinations. The specific details will differ, but the basic ingredients remain the same. What can change is how often those ingredients come together and how much energy and moisture are available when they do. As the atmosphere warms overall, one of the most consistent signals is an increase in the amount of water vapour it can hold. This doesn't automatically mean that every storm will be stronger or wetter, but it does mean that the potential for heavier precipitation exists when conditions are right. For winter storms, this creates an interesting set of possibilities. In regions that remain cold enough for snow, storms may have access to more moisture, which can translate into heavier snowfall. In regions that hover near freezing, storms may more often produce a mix of rain, snow, and ice, with a greater risk of freezing rain events. Fern's varied precipitation types offered a glimpse of this kind of complexity. The storm moved through temperature zones that were finely balanced, and small shifts led to very different outcomes in different places. This sensitivity is likely to remain a defining feature of winter storms in a warming climate. Another lesson from Fern involves movement, or sometimes the lack of it. The storm's pace was influenced by the shape of the jet stream and the placement of surrounding pressure systems. When the upper-level winds took a slower, more winding path, the storm lingered. If patterns that favour slower, more meandering jet streams become more common, future storms may also be more likely to persist over a region for longer periods. This doesn't necessarily mean that storms will always be stronger, but it does mean that their impacts could be prolonged. A slow-moving storm can be just as disruptive as a very intense one, simply because it keeps delivering weather to the same area. Hours of steady snow can add up. Repeated rounds of freezing rain can build layers of ice. Continuous wind can reshape drifts and stress infrastructure. Fern's lingering presence in some regions highlighted how duration can be as important as intensity. This is a factor that forecasters and planners increasingly pay attention to, especially when assessing the potential for extended disruptions. There is also the matter of storm tracks. The paths that storms follow are shaped by the large-scale flow of the atmosphere. Changes in that flow can alter which regions tend to see more frequent storms and which tend to see fewer. Over long periods, shifts in ocean temperatures and atmospheric pressure patterns can nudge these tracks northward or southward. This can change the typical winter experience of a region. An area that once saw frequent snowstorms might see more rain. Another might find itself in the path of more frequent cold air outbreaks. Fern followed a path that brought it into contact with both cold and warm air, allowing it to produce a range of impacts. Future storms may follow similar or different routes, depending on how the broader patterns evolve. What Fern also illustrates is the importance of boundaries. The most active parts of the storm were often found near the dividing lines between air masses. These boundaries, where warm and cold air meet, are where energy is most readily released. As climate patterns shift, the location and strength of these boundaries may also change. This could influence where the most intense parts of storms tend to set up. Regions that are currently on the edge of typical storm tracks might find themselves more often under the most active zones, or less often, depending on how those tracks move. Another aspect that Fern brings into focus is the interaction between storms and the built environment. Roads, power systems, buildings, and communication networks all respond to snow, ice, and wind in specific ways. The impact of a storm is not just about the weather itself, but about how that weather intersects with human systems. As populations grow and infrastructure expands, the potential for disruption can increase, even if the storms themselves do not become more frequent or more intense. A storm that would have passed largely unnoticed a century ago can have significant consequences in a densely populated, interconnected region. This means that learning from Fern is not only about understanding atmospheric processes, it's also about understanding vulnerabilities. Where did power outages occur? Which roads became impassable? Which communication systems were strained? These observations can inform future planning, from how utilities reinforce lines to how cities manage snow removal and emergency response. In this sense, each storm becomes a kind of stress test for the systems people rely on. There is also a social dimension to how storms are experienced and remembered. Fern's name, its coverage in the media, and the stories people told about it all contribute to a shared memory. These memories shape expectations. They influence how people respond to future forecasts, how seriously they take warnings, and how they prepare. If a region experiences a particularly disruptive storm, people may be more cautious the next time a similar system is predicted. This can lead to better preparation and reduced impact, even if the storm itself is comparable. On the scientific side, Fern contributes to the ongoing effort to improve models and forecasts. Every storm provides an opportunity to compare what was predicted with what actually happened. Where do the models perform well, where do they struggle? For example, if Fern intensified more quickly than most model runs suggested, scientists can examine why. Was moisture underestimated? Was the jet stream's influence misrepresented? Were certain small-scale features not captured well enough? These questions lead to refinements in the models, improvements in data assimilation, and better understanding of key processes. Over time, this can expand the window of confident prediction, giving people more notice before a storm arrives. Fern also highlights the value of ensemble forecasting. The range of possible outcomes that models produced in advance reflected the atmosphere's sensitivity. By examining which scenarios played out and which did not, scientists can learn more about how certain patterns evolve and which signals are most reliable. This kind of learning is cumulative. It doesn't come from a single storm, but from many compared and contrasted over time. Fern is one piece in that larger puzzle. Another lesson involves communication. How forecasts are presented can influence how people perceive and respond to risk. Clear explanations of uncertainty, potential impacts and timing can help people make informed decisions. Fern's evolving forecast, with its gradual shift toward a more intense scenario, is an example of how communication needs to balance caution with clarity. Too much confidence too early can lead to unnecessary alarm. Too little emphasis on potential impacts can leave people unprepared. Finding that balance is an ongoing challenge, and each storm offers feedback on how well it was achieved. From a broader perspective, Fern invites reflection on how storms fit into the changing climate system. While it's not possible to attribute a single event directly to long-term trends, it is possible to examine how those trends might influence the kinds of storms that are more likely in the future. As we discussed earlier, a warmer atmosphere can hold more moisture. This can increase the potential for heavy precipitation. Warmer oceans can provide more energy to storms. Changes in temperature gradients can influence the behavior of the jet stream and the movement of pressure systems. Together, these factors suggest that the character of winter storms may continue to evolve, not necessarily in a simple, linear way, but in a complex pattern of shifting frequencies, intensities, and types of impacts. Fern's combination of snow, ice, and wind is a reminder that winter storms are multifaceted. They are not just about how much snow falls, they're about how temperature changes with height, how long conditions persist, how strong the winds become, and how all of these elements interact. Future storms may continue to present these kinds of layered challenges. A storm might not break snowfall records, but it might produce widespread ice. Another might move slowly, delivering moderate snow over a long period. Another might bring strong winds that amplify the effects of whatever precipitation falls. In this sense, the idea of severity becomes more nuanced. It's not just about one number on a chart, it's about the combination of factors and how they play out in real places. Fern also underscores the importance of regional differences. The same storm can be experienced very differently across its path. One area might see a picturesque snowfall, another might deal with power outages and hazardous roads. These differences are shaped by local geography, infrastructure, and the precise position of the storm's internal boundaries. As climate patterns evolve, these regional differences may become more pronounced. Some areas may see a shift toward more frequent heavy snow events. Others may see a rise in ice storms. Others may find that winter storms become less common, but more disruptive when they do occur. This patchwork of experiences can make it challenging to talk about winter storms in general terms. The story is always local, even when the patterns behind it are global. Fern's story also touches on the concept of resilience. How quickly did communities recover? How adaptable were systems to changing conditions? How well did communication channels function? These questions are increasingly important as weather variability continues to pose challenges. Building resilience is not just about withstanding a single storm. It's about creating systems that can handle a range of conditions and recover quickly when disruptions occur. In this way, Fern becomes part of a larger narrative about how societies interact with the natural world. Storms test not just the atmosphere's dynamics, but also the ways people organise, plan, and respond. There is also a quieter, more reflective lesson in Fern's story. It's a reminder of how interconnected the planet is. A storm that affects one region is shaped by conditions in others. Moisture from distant oceans, cold air from faraway latitudes, winds guided by patterns that circle the globe. This interconnectedness means that changes in one part of the system can have far-reaching effects. It also means that understanding future storms requires a global perspective, one that looks beyond local conditions and considers the broader flow of energy and air around the planet. As researchers continue to study these connections, they build a more detailed picture of how the climate system operates. They examine how ocean currents, ice cover, atmospheric circulation, and human activities interact. They test how well models capture these interactions and look for ways to improve them. Fern as a single event is a small piece of this vast research effort, but it is a tangible one. It's a storm that people experienced, that left marks on landscapes and memories. It's a case study that can be revisited, analysed and compared to others. In thinking about what Fern tells us about future storms, it can be helpful to hold on to a sense of both continuity and change. The basic physics of the atmosphere are not shifting. Warm air will still rise, cold air will still sink, pressure differences will still drive winds, moisture will still condense into clouds and fall as precipitation. At the same time, the context in which these processes play out is evolving. The background temperature, the distribution of moisture, the extent of ice and snow, and the behaviour of large-scale circulation patterns are all subject to change. Future storms will be shaped by this evolving context, even as they follow the same fundamental rules as Fern. There's a kind of quiet humility in this realisation. We can learn from storms, we can improve our ability to anticipate and respond to them, but we're also part of a system that is larger and more complex than any single model or theory can fully capture. Fern's legacy, in this sense, is not just a set of data points or a place in a seasonal list of named storms. It's a reminder of the atmosphere's capacity for both pattern and surprise, for order and variation. As you think about the future, you might imagine storms yet to come, each with its own path, its own mix of snow, ice, wind, and rain. Some will be remembered, others will pass quietly. All will be part of the same ongoing exchange of energy that has been shaping weather for as long as the planet has had an atmosphere. At some point, when you step back far enough from the details of a single storm, the story begins to widen. Fern becomes less about a specific set of snow totals or wind speeds, and more about the realization that everything we've been talking about exists inside a system that never truly pauses. The air is always shifting, heat is always moving, water is always changing form and location. Even on the calmest, clearest day, the same processes that shaped Fern are still quietly at work, just arranged in a gentler pattern. Living inside this system is something most of us do without thinking about it very often. We notice the weather when it interrupts our plans, when it surprises us, or when it turns a familiar place into something that feels new. But most of the time, the atmosphere is simply there, a background presence that we move through without much reflection. And yet, every breath you take is part of that system. The air in your lungs was not long ago somewhere else. It may have drifted over a forest, crossed a body of water, passed through a city, or descended from higher altitudes. It carries with it traces of where it's been, in temperature, moisture, and composition. You are, in a very literal sense, connected to the movement of the atmosphere every moment you exist within it. Storms like Fern make that connection harder to ignore. They bring the motion of the system into sharper focus. Wind pushes against your body. Cold air stings your skin. Snow and ice change the ground beneath your feet. The invisible becomes tangible, but the same flow is there when the sky is blue and the air is still. High above, winds continue to move. Far away, pressure systems rise and fall, oceans release heat into the air, and land absorbs it back again. The planet is always engaged in this quiet exchange. One way to think about it is as a kind of circulation, not just of air, but of energy. The sun provides most of the energy that drives the system. It warms the surface of the Earth unevenly, more at the equator, less toward the poles. That uneven heating creates differences in temperature, and those differences create movement. Warm air rises, cold air sinks, pressure differences form, Winds flow, moisture evaporates, condenses and falls. Each step is connected to the next, forming a loop that never really closes because the sun keeps adding energy to the system day after day. Fern was one expression of that loop, a moment when the flow of energy became organised in a way that produced strong winds, heavy precipitation and noticeable impacts. But even as Fern dissipated, the loop continued. The energy that fueled the storm didn't vanish. It was redistributed, spread out, carried onward by the moving air. This perspective can change how you think about weather. Instead of seeing it as a series of separate events, you can start to see it as a continuous process, with each day flowing into the next, each pattern giving way to another. There's a quiet elegance in that continuity. The atmosphere doesn't reset at midnight. It doesn't start over when a storm ends. It carries the imprint of what came before into what comes next. A storm can cool the air behind it. It can alter the moisture in the soil. It can change the temperature of the ocean surface slightly. These changes, in turn, influence the conditions for the next system that comes along. In this way, weather is a kind of memory, not a conscious one, but a physical one. The state of the atmosphere at any given moment reflects the cumulative effects of what has happened recently, layered on top of the broader patterns that have been developing over longer periods. Living inside this system means that we are always responding to it, even when we're not aware of doing so. Our clothing choices, our building designs, our daily routines, and even our cultural traditions are shaped, in part, by the patterns of weather and climate in the places we live. In colder regions, homes are built to retain heat. In warmer regions, they are built to encourage airflow. In places with heavy snowfall, roofs are angled to shed snow. In places with strong winds, structures are reinforced to withstand them. These design choices are, in a sense, conversations with the atmosphere. They reflect an understanding developed over time of how the system tends to behave in a particular place. Storms like Fern can feel like interruptions to that understanding, moments when the system pushes beyond what is expected or comfortable. But they also reinforce the idea that the atmosphere is not static, that it can and will present a range of conditions over time. There's also a temporal aspect to living inside a moving system. We experience weather in moments, hours and days. The atmosphere operates on scales that range from minutes to decades. A gust of wind can last a few seconds. A pressure pattern can persist for weeks. An ocean temperature trend can last for years. Our personal experience sits at the smallest end of that range. We feel the wind on our face, but we don't feel the slow drift of a jet stream over thousands of miles. We notice a sudden temperature drop, but we don't directly sense the gradual warming or cooling of the oceans. Storms like Fern bridge that gap. They are events that are large enough and intense enough to hint at the broader patterns behind them, even if we don't consciously trace those connections. When you watch a weather map showing a storm's path across a continent, you're seeing a snapshot of that larger movement. You're seeing how air masses and pressure systems interact over space and time, creating a kind of choreography that plays out above and around the surface of the Earth. This choreography is shaped by the planet itself. The rotation of the Earth bends winds. The distribution of land and water influences how heat is absorbed and released. Mountain ranges redirect airflow. Ice and snow reflect sunlight. Forests and deserts interact differently with heat and moisture. Every feature of the planet adds a subtle influence to the flow of the atmosphere. Fern's path, like the path of any storm, was shaped by these influences, even if most of them were far from where the storm's impacts were felt most strongly. Living inside this system also means that we are part of the feedback loops that shape it. Human activities can influence the atmosphere in ways that extend beyond local weather. The release of greenhouse gases alters how much heat the planet retains. Changes in land use affect how much sunlight is absorbed or reflected. Urban development changes how air moves near the surface. These influences operate on longer timescales than a single storm, but they shape the environment in which storms form and move. They become part of the background conditions, part of the stage that future systems will step onto. This doesn't mean that every storm is a direct result of human activity. The atmosphere has been producing storms for as long as it has existed. But it does mean that the context in which those storms occur is influenced by the cumulative effects of what happens at the surface. From a philosophical point of view, this can create a sense of both connection and responsibility. Connection, because it highlights how deeply intertwined human life is with the natural systems of the planet. Responsibility, because it suggests that our collective actions can influence the conditions those systems operate under. There is also a sense of scale that comes into focus when you think this way. The atmosphere is vast. It wraps around the entire planet. The oceans are deeper and wider than anything humans have built. The energy flowing through these systems is immense, and yet the experience of that vastness often comes down to small personal moments. The sound of snow underfoot, the warmth of a coat against cold air, the sight of clouds moving across the sky. These moments are points of contact between the individual and the global, between the local and the planetary. Fern's story was made up of countless such points of contact, experienced by different people in different places, each forming their own memory of the same system in motion. Another way to think about living inside a moving system is in terms of cycles. Water cycles between ocean, atmosphere and land. Carbon cycles between air, plants, soil and rock. Energy cycles from the sun to the earth and back into space. Weather is part of these cycles. It's the visible, felt expression of how they interact at a given moment. Fern was part of the water cycle. Moisture evaporated from the ocean, travelled through the air, condensed into clouds and fell as snow and ice. That water then returned to the surface, eventually melting, flowing into rivers and making its way back to the sea. It was also part of the energy cycle. Heat from the sun, stored in water and land, was released into the atmosphere, moved around by winds and radiated back into space. These cycles don't have clear beginnings or endings. They are continuous, overlapping and interdependent. A storm is a moment when several of them intersect in a particularly noticeable way. There's something quietly humbling about that. It suggests that what we often think of as the weather is really just one layer of a much deeper set of processes, all unfolding at once. Living inside this system can also influence how we think about time. We tend to mark time in human terms: days, weeks, years. The atmosphere has its own rhythms, seasonal shifts, multi-year oscillations, long-term trends. A winter storm fits into a season fits into a year fits into a climate record that stretches back through history. Fern occupies a small place in that record. It's one event among countless others, and yet, for the people who experienced it, it may feel large, even significant. This contrast between personal scale and planetary scale is one of the more intriguing aspects of living on Earth. The same system that shapes global climate patterns also shapes the weather on your street on a given afternoon. There's also a sense of adaptability that comes with this perspective. Humans have always adapted to the conditions of the places they live. Clothing, architecture, agriculture, and social practices all reflect an ongoing adjustment to the environment. As the system continues to move and change, that process of adaptation continues as well. Some changes are small and incremental, others require more deliberate planning and response. Storms like Fern can act as prompts for this adaptation. They highlight vulnerabilities. They reveal which systems are resilient and which are strained. They encourage changes, whether in infrastructure, policy, or personal behaviour. This doesn't mean that every storm leads to a transformation. Often, life returns to normal, and the memory of the event gradually fades. But over time, the accumulation of experiences can lead to shifts in how communities prepare and respond. There is also an emotional aspect to living inside a system that never stops moving. Weather can influence mood, memory, and perception. A sunny day can feel uplifting. A long stretch of cold, grey weather can feel heavy. Storms, in particular, can leave strong impressions. They can be associated with moments of challenge, of disruption, of coming together, or of quiet reflection. Fern's story likely contains all of these elements for different people. For some, it may be remembered as a time of inconvenience or difficulty. For others, it may be remembered as a moment of beauty or stillness. These subjective experiences are part of the system as well, not in a physical sense, but in a cultural one. They shape how weather is talked about, remembered, and anticipated. In a way, living inside the atmosphere means living inside a story that is constantly being written and rewritten. The characters are air masses, oceans, pressure systems, and sunlit surfaces. The plot is the ongoing exchange of energy and matter. The chapters are storms, calm periods, seasons, and years. We don't get to choose the direction of that story, but we do get to experience it, interpret it, and respond to it. Fern was one scene in that larger narrative. It had its own arc, its own set of conditions, its own impacts. Now that it has passed, the narrative continues, shaped by the same forces that brought it into being. As you think about living inside this system, it can be helpful to imagine the atmosphere not as something above you, but as something you are inside of. It surrounds you, moves through you, and connects you to places far beyond your immediate view. The wind that brushes past your face may have crossed mountains or oceans. The moisture in the air may have evaporated from a distant body of water. The temperature you feel may be influenced by sunlight absorbed thousands of miles away. These connections exist whether or not you notice them. Storms like Fern simply make them more visible, more tangible, more difficult to ignore. There's a certain quiet comfort in this idea as well. Even when the weather is harsh or disruptive, it's part of a system that is, at its core, about balance. The atmosphere is always moving toward a state where energy is more evenly distributed. It doesn't always get there smoothly. The path involves swings, surges, and sometimes storms. But the underlying tendency remains. Living inside a system that never stops moving means living inside a process of continual adjustment. It means that no condition, whether calm or stormy, is permanent. Change is the constant. Fern's story, in that sense, is not about a beginning and an end. It's about a moment of heightened motion within an ongoing flow. After the last flakes have settled and the strongest gusts have eased, there is often a moment when the world feels as if it has exhaled. It's not a sharp, sudden silence. It's a gradual softening, a gentle lowering of the volume on everything that was loud just hours before. Fern's story, like the story of every storm, eventually arrives at this quieter place, where motion gives way to something that feels closer to stillness, even though the system itself never truly stops moving. In the hours following the storm's passage, the atmosphere begins to rearrange itself again. The low-pressure centre that once drew in air and lifted it skyward loses its structure. The rising motion weakens, the outflow aloft fades. At the surface, the pressure slowly increases as air settles back down. Winds, once driven by strong gradients, find less reason to hurry. This change doesn't happen all at once. It unfolds in stages. First, the bands of heavier precipitation break apart. Snow becomes lighter, more intermittent. Freezing rain transitions to drizzle or stops entirely. The wind, which may have been a constant presence, begins to come in waves instead of a steady push. For someone standing outside, this can feel like a shift in mood, rather than a clear line between storm and calm. The air might still be cold, the sky might still be overcast. But the sense of urgency in the movement is gone. One of the most noticeable changes is often in the soundscape. During the storm, the wind filled the air with a continuous rush or howl. Snow or sleet tapped against windows. Branches creaked under the combined weight of ice and motion. Afterward, those sounds recede. What remains might be the distant hum of a plough, the occasional drip of melting ice, or simply the quiet presence of a changed landscape. Snow absorbs sound, and when it lies fresh and undisturbed, it can make even busy places feel muted. Streets that usually echo with traffic noise can feel hushed, as if the world has been wrapped in a soft layer of insulation. This quiet can be one of the most memorable parts of a winter storm's aftermath. It's a kind of pause, a moment when the pace of things seems to slow, even if only briefly. Visually, the shift is just as striking. The sky often clears from the back edge of a storm, revealing a different quality of light. In winter, that light can be sharp and bright, reflecting off snow and ice in a way that makes the world seem more defined. Ice-coated branches catch the sun and scatter it in small flashes. Snowbanks take on subtle shades of blue and grey in the shadows. Even familiar buildings and streets can look new, their edges softened or reshaped by what fell from the sky. This change in appearance is not just cosmetic, it's a sign of how the storm has altered the surface of the world, at least temporarily. The ground is colder or warmer than it was before. The moisture content of the soil has changed. The balance between reflected and absorbed sunlight has shifted. All of these small changes feed back into the atmosphere. Snow-covered ground reflects more sunlight, keeping the air above it cooler. Bare patches absorb more heat, creating small pockets of warmth. These contrasts can influence the movement of air near the surface, setting up gentle breezes or subtle temperature differences that weren't there before. In this way, the storm leaves behind more than a memory. It leaves behind new conditions, new starting points for whatever weather comes next. There is often a practical side to this period of stillness as well. People venture out to assess what the storm has left. They clear paths, dig out vehicles, check for damage, and reconnect with neighbours. This activity can bring a different kind of energy to the quiet landscape, one rooted in response rather than anticipation. In some places, the aftermath of Fern may have involved dealing with power outages, fallen branches or icy roads. In others, it may have been as simple as brushing snow off a doorstep, or enjoying the way a familiar park looked under a fresh layer of white. These responses are part of the storm's extended life, the phase where its effects are felt even though its core has moved on. From an atmospheric perspective, this period is marked by the arrival of a different kind of air mass. Often, behind a winter storm, there is a push of colder, drier air. This air is associated with higher pressure and more stable conditions. It tends to sink rather than rise, suppressing cloud formation and allowing skies to clear. This sinking motion is the opposite of what drives a storm. Where Fern was about air converging and lifting, the aftermath is about air spreading out and settling. The clarity that often follows a storm is a direct result of this. With less rising motion, there are fewer clouds. With less moisture in the air, visibility improves. The horizon feels farther away. Cold, dry air also changes how the world feels on your skin. It can be sharp and crisp, carrying scents more distinctly. It can make your breath visible in the air, a small personal reminder of the temperature difference between your body and the environment around you. This kind of air mass can linger for days, maintaining a sense of calm and stillness. But even as it does, the larger system is already beginning to shift again. High-pressure systems don't stay in one place forever. They drift, weaken, or are pushed aside by the next set of changes in the broader flow of the atmosphere. Somewhere far away, another low-pressure area may be forming. Another boundary between warm and cold air may be sharpening. The stillness after a storm is, in this sense, a temporary arrangement. It's a phase in a continuous cycle, not a final state. There is something quietly reflective about this moment, though. The contrast between what was and what is can make you more aware of the system's movement. You remember the wind because it's no longer there. You notice the quiet because you can compare it to the noise that came before. This contrast can also make the environment feel more tangible. You see the tracks in the snow. You notice the way ice clings to certain surfaces and not others. You observe how sunlight falls differently across a changed landscape. These observations are small, but they connect you to the larger story of the storm. They are points where the abstract processes we've been talking about, pressure systems, jet streams, moisture pathways, become something you can see and touch. There is also a sense of closure that often accompanies this phase, even though the larger narrative continues. The storm that was the focus of attention has passed, the alerts have ended, the forecasts have moved on to whatever comes next. But closure doesn't mean erasure. Fern's presence lingers in subtle ways, in the shape of snowbanks along roads, in the patches of ice that take longer to melt in shaded areas, in the stories people tell about what they experienced. These lingering traces can last for days or weeks, depending on the temperature and the amount of sunlight. They are reminders that the storm was there, even as the system that created it has moved on. On a broader scale, the atmosphere also carries its own traces of the storm. The redistribution of heat and moisture during Fern's passage altered the balance of energy in the regions it affected. Cold air was pushed into some areas, warmer air was drawn into others, moisture was moved from the ocean to the land. These changes become part of the initial conditions for the next phase of weather. The atmosphere's memory in this physical sense is short, but it is not non-existent. What happens today influences what can happen tomorrow. This idea of drifting towards stillness is not just about the end of a storm, it's about the way the system transitions between different states. From active to calm, from organised to diffuse, from focused motion to broader, gentler flow. These transitions are where much of the atmosphere's character is revealed. They show how the system responds when the forces that once drove it weaken or change direction. There is also a human dimension to this drift. During a storm, attention is often focused outward. People check forecasts, watch the sky, listen to the wind. Afterward, attention can turn inward or toward a routine again. The return to normal activities, work, school, errands, carries a different feel when the environment has just gone through a dramatic change. There can be a sense of appreciation for the calm, or a lingering caution in how people move through icy or snowy spaces. In some cases, the stillness after a storm can create a moment of connection. Neighbours help each other shovel. People share updates and experiences. There's a brief sense of collective response, of having gone through something together, even if that something was simply a shared change in the weather. This social layer is not part of the atmosphere's mechanics, but it is part of the storm's story. It's how the event comes woven into memory and community. As the days pass and temperatures fluctuate, the physical signs of Fern gradually fade. Snow melts, ice breaks away. Surfaces return to their usual colours and textures. The landscape shifts back toward what feels normal, but normal itself is just another temporary state. It's the arrangement of conditions that happens to exist at that moment, shaped by what came before and ready to be reshaped by what comes next. From a scientific perspective, this is one of the most important ideas to hold on to. The atmosphere is not a machine that switches on and off. It's a fluid system, always in motion, always adjusting. The stillness after a storm is not an absence of movement. It's a different pattern of movement, one that is less intense and less obvious. High above, winds continue to flow. Pressure systems continue to shift. The jet stream continues its long winding path. Oceans continue to exchange heat with the air. The sun continues to add energy to the system each day. All of these processes are ongoing, even when the surface of the world feels quiet. In this way, drifting towards stillness is as much about perception as it is about physics. It's about how we experience the system when it moves more gently, when its effects are less dramatic. There is a kind of rhythm to this experience, activity and calm, change and pause, storm and clear sky. This rhythm is not perfectly regular. Sometimes storms come in quick succession, sometimes calm stretches on. But the alternation between more and less intense phases is a fundamental part of how the system expresses itself. Fern was one peak in that rhythm. The stillness that followed was the valley. From a longer-term perspective, these peaks and valleys blend into the larger patterns of seasons and climate. Winter gives way to spring, spring to summer. Each season has its own typical rhythms, its own balance between calm and activity. Fern's story fits into that seasonal flow. It was a winter storm shaped by cold air, warm water, and a dynamic jet stream. The stillness that followed was part of winter's quieter side, a phase where the atmosphere settled into a more stable pattern, at least for a time. As you think about this, it can be helpful to imagine the atmosphere as a kind of breathing system. Storms are like deep, energetic breaths. Calm periods are like slower, quieter ones. The system never stops breathing, but the pace and depth change. Living inside that breathing system means being part of those changes, even if we don't always notice them. There's also an element of anticipation that returns with the stillness. Once a storm has passed, the question of what comes next naturally arises. Will the calm last? Will another system form? Will temperatures rise or fall? This anticipation is part of the ongoing relationship between people and weather. It's why forecasts continue to be checked even when the sky is clear. It's why conversations about the weather persist, even when nothing dramatic is happening. Fern's departure doesn't close the book on the season. It turns the page. Somewhere, another low-pressure system is beginning to take shape. Another boundary between warm and cold air is forming. Another section of the jet stream is bending or straightening. These changes are happening whether or not they will lead to another storm, whether or not they will become noticeable at the surface. The stillness after Fern is, in this sense, a moment between stories. The previous one has ended. The next one is not yet visible. There is a certain openness in that moment. The landscape is changed, but the future is not yet defined. The atmosphere is in a state of transition, carrying the imprint of what has just happened and the potential for what might happen next. From a reflective point of view, this can feel like a natural place to pause, to take in the world as it is in that brief window of calm. You might notice the way light falls on snow, the way breath forms a small cloud in cold air, the way sound carries differently in a quiet environment. These small details are easy to overlook when the weather is dramatic. They become more noticeable when the pace slows. In a broader sense, they are reminders of the scale of the system we live within. The same processes that drive powerful storms also create these quiet moments. The same flow of energy that fuels wind and snowfall also shapes the gentle patterns of clouds on a calm day. Fern's story, from its formation to its intensification to its fading, is a single thread in that larger tapestry. As you drift toward this sense of stillness, it can be comforting to remember that nothing in the system is truly final. Conditions change, patterns evolve, motion continues, even when it's not immediately apparent. The atmosphere doesn't stop at the end of a storm, it carries on, shaping the next set of conditions, the next set of experiences, the next chapter in the ongoing interaction between sky and surface. Fern has become part of that ongoing flow, its energy redistributed, its moisture returned to the cycle, its memory woven into the record of the season. What remains now is the quieter phase, the gentle movement that follows the storm's peak, the space where the world feels, for a time, more settled. And within that space, the larger system continues its work, slowly, steadily, preparing the ground, the air and the sky for whatever form of motion comes next, just beyond the edge of this moment of calm.